In the vastness of the cosmic night, a silent storm is brewing beyond our sight. There are lights in the sky our eyes cannot see, waves of energy far beyond the violet end of visible light. Among these unseen lights are gamma rays, the highest energy light in the universe. They slip through space like invisible fire, carrying whispers of exotic worlds and violent events. Unlike the gentle glow of the sun or the stars, these rays are hidden from us. They pass through windows and even our own bodies without us noticing. Only with special instruments can we detect their presence, as if listening for a secret murmuring across the cosmos. Imagine a rainbow that starts at the color violet and then keeps going beyond blue, beyond ultraviolet, into shades we cannot name. At the end of that rainbow would be gamma rays. Just as ultraviolet light can give us sunburn and infrared light can keep us warm, gamma rays have effects too. But because they are so penetrating, they pass right through things, carrying news from where they came. They are the messengers from the most extreme places, arriving in silence, to be caught by our instruments. Our ordinary senses reveal only part of reality. We see visible light, but imagine if you had infrared vision, radio hearing, or the ability to feel gamma rays. Gamma rays are light that's more energetic than the X-rays that doctors use. In the lab, gamma rays can knock electrons out of atoms. In space, they might change the structure of molecules. Despite this potential power, Earth's atmosphere protects us, absorbing gamma rays before they can reach the ground. That's why we had to look to space itself to study them. Space-based observatories became our eyes into this hidden realm. For most of human history, our night sky seemed filled only with the familiar stars and planets. Yet above and beyond the twinkling stars, there is a whole world of light we cannot see. Imagine a cosmic rainbow that stretches far beyond the colors we know. At the hidden end of that rainbow lie gamma rays, the fiercest and most energetic kind of light. Even though they are all around us, our eyes are blind to them. They do not paint the sky with visible colors. Instead, they pass through our atmosphere and bodies, unseen and unfelt. On Earth, we learned about gamma rays in the 20th century, from powerful radioactive materials in laboratories. But it was only when we ventured into space that we realized the universe itself held gigantic gamma ray phenomena. These eruptions of energy are not only invisible, they are among the deadliest and most energetic events known. To imagine their scale, think of a burst of lightning so brilliant and powerful, it could burst unseen across galaxies. They are like cosmic lighthouses flashing on and off in the midnight sky. The discovery of gamma rays was itself a feat of ingenuity. In the early 1900s, scientists in laboratories noticed a strange radiation coming from radioactive elements. They called it gamma radiation. But that was only the beginning. Gamma rays were not just found in atoms on Earth. The cosmos, it turned out, was also full of them. Every time a star dies in a supernova, or a black hole feasts on gas, it may hurl out gamma rays. These cosmic gamma rays journey across space to reach us, if we only have the tools to catch them. We have built special telescopes and satellites to see gamma rays. They orbit high above us, because gamma rays cannot penetrate our atmosphere. When they arrive, these detectors register a flash or a signal. In a sense, we are building new senses, turning the invisible into the audible. Thanks to these instruments, the sky is no longer silent. We can hear the murmurs of exploding stars and colliding moons carried by gamma rays. Even now, as we speak, faint gamma rays are passing through you and me, unnoticed. They come from all directions, from the sun's occasional flares, from distant galaxies, and even from cosmic rays hitting Earth's atmosphere. The more we explore the universe in gamma rays, the more we realize the cosmos is alive with energy beyond sight. Yet among all these gamma emissions, some bursts stand out above the rest. They are the mystery we seek to explore, titanic flashes that glow across the hidden tapestry of the sky. All of this may seem fantastical, but it is rooted in real discovery. The scientists and engineers who ventured into this unknown did so without knowing what they'd find. They built telescopes that see in gamma rays, the way night vision goggles see in infrared. And when those instruments turned on, the quiet night sky was transformed. Now, each time we talk about gamma ray bursts, we remember that discovery is an adventure in its own right. For now, these hidden blasts of energy remain silent secrets of the cosmos. In the coming decades, however, human ingenuity would catch the faint tremors of these invisible storms. Our journey into understanding this hidden fire began with strange signals from the darkness, whispers caught by instruments far above Earth. It was the mid-1960s, an era of suspicion and secrets. The United States and the Soviet Union were locked in a tense standoff, each side wary of hidden nuclear tests by the other. To enforce a new test ban treaty and keep peace, scientists and engineers built watchful eyes in space. These were the Vela satellites, pairs of silent sentinels whose job was to listen for the distinctive flash of a nuclear bomb in space or high in the atmosphere. The first Vela satellites were launched in 1963. They carried instruments tuned to gamma rays and X-rays, because those energetic flashes would announce a clandestine nuclear detonation. They circled Earth far beyond the reach of ordinary satellites, in high orbits. The engineers who built them imagined their satellites silently watching for human-made fireworks in the sky, not events from the distant cosmos. And yet, in July 1967, two of those satellites recorded something astonishing. On July 2nd, 1967, the Vela satellites detected a flash, unlike any they were meant to see. The satellites sensed a burst of gamma rays that lasted only a fraction of a second. It was brief, but undeniable, a pulse of energy beyond anything expected from a nuclear test. At first, there was confusion. Was it a secret test by some hidden power, or something unknown? The data was puzzling enough that the researchers at Los Alamos held it in confidence, unsure how to interpret it. The Vela satellites were not built to dazzle the sky, but to police it. They orbited in silence, untouched by human presence, scanning for any sign of gamma rays. Each satellite was loaded with detectors and recording systems. When an unexpected flash occurred in 1967, it was like a note out of place in a familiar tune. Yet the scientists who saw it did not shout. They quietly puzzled over the data. Those scientists had to be detectives. They wondered if some secret bomb test was being hidden. The team compared the gamma signal to known signatures of nuclear detonations. It was different. Instead of triggering alarms on Earth, this flash was innocent of any human origin. It came from the sky, beyond where any of our weapons could reach. The idea that something beyond Earth could create it was still unbelievable. This puzzling discovery was the beginning of a new mystery. The team at Los Alamos quietly filed away the data, intrigued and perplexed. Over the next few years, the satellites recorded dozens more of these strange bursts. Each time, the signal was brief and brilliant, leaving the scientists searching for answers. Each new data point deepened the riddle. As multiple Vela satellites flew in formation, they could compare the exact arrival times of a burst at different spacecraft. This let them triangulate a rough location in the sky. But year after year, the bursts pointed everywhere, at all corners of space, not to any known source, no pattern, no repeat location. Every time it seemed they were about to find a clue, another burst upended their hopes. Over the next few years, the Velas found more of these flashes. Each time, a satellite would pick up a brief burst, trigger a recording, and then fall silent. As the secret logs grew thicker, the Los Alamos team, including scientists like Ray Klebersaddle, sifted through the recordings. By triangulating signals from different satellites, they could roughly estimate that the bursts did not come from Earth at all, but from far beyond. By 1973, they were ready to publish their findings. They had discovered a new cosmic mystery. When the news eventually reached the wider world, it was a sensation. Astronomers around the globe realized that something extraordinary was happening overhead at unpredictable moments. There was no pattern to these flashes in time or space. They just appeared unexpectedly. What began as a mission to monitor terrestrial tests had stumbled upon signals from the vast cosmos. The discovery of gamma-ray bursts opened a new window on the universe, one that humans had only just cracked open. In the calm of observatories and research institutes, many treated these findings with a bit of skepticism at first. Could this really be a cosmic phenomenon? But as more bursts showed up, the evidence became undeniable. One by one, teams around the world began to listen in. Observatories repurposed instruments, satellites were trained, and sky monitors were tuned to catch the next flash. So began an era of cooperative astronomy, as teams around the globe coordinated observations to chase down the fleeting gamma-ray flash. Looking back, it was almost poetic luck. The very same sensors put in place to stop a nuclear holocaust had stumbled upon a relic of the cosmos's most violent moments. It was a reminder that our search for one thing, safeguarding Earth, can sometimes reveal something entirely different, unlocking cosmic secrets. The era of the space race had turned eyes outward in unexpected ways, and now it would help us look beyond humanity's horizon. Soon, even science fiction writers and amateur enthusiasts speculated about these cosmic fireworks. In newspapers and magazines, the mysterious bursts began appearing as headlines, mysterious cosmic flashes, and signals from space. At the same time, in observatories from California to the Canary Islands, researchers prepared their telescopes and instruments, hoping to catch afterglows or signals that might accompany the gamma flashes. It was as if the whole world had become alert, waiting for the next flash of inspiration from the sky. Within the scientific community, the discovery of these bursts sparked a blend of excitement and skepticism. Many observatories and universities prepared to chase after the next flash, eager to know more. Yet for now, as the Velas continued their vigil, the bursts remained rare and mysterious. Scientists knew only that these flashes had been found, and they waited patiently, curious for the next flicker of the unseen storm. In the hush after those first detections, scientists knew one thing for sure: something incredible was happening overhead. The darkness of space, once thought empty, was suddenly alive with these bursts of light. Astronomers waited in quiet anticipation for the next flash. They did not yet know what the bursts were, but they had opened a new window onto the cosmos. As more satellites and detectors went to work, scientists began to see a pattern. The gamma-ray bursts arrived suddenly, like flashes from nowhere. A detector might record a brilliant burst of gamma rays for just a few seconds, and then nothing. The sky would go silent again, as if nothing had happened. The telescopes and detectors that hunted these bursts operated in quiet vigilance. Some missions, like NASA's Compton Gamma Ray Observatory, scanned the entire sky continuously, alert for any flicker of gamma light. Whenever a burst happened, the detectors clicked or flashed, recording the event's time and intensity. It was as if the universe whispered its secret out of nowhere, and these instruments were the devoted listeners. With each new year, more bursts were found. In fact, as sensitive satellites kept watch, the tally of gamma-ray bursts rose into the hundreds. They seemed to occur randomly, often several times per week. To the bewildered astronomers, the sky was no longer a quiet canvas. Instead, it pulsed with hidden fireworks. Yet to us on Earth, the night remained dark and calm. Only the instruments knew the storminess that the sky could hide. These bursts were unpredictable and fleeting. Some lasted just a fraction of a second, like a brief spark. Others blazed for a few minutes, an eternity compared to a blink of an eye on cosmic scales. Yet each one was extraordinarily bright during that instant, sometimes outshining whole galaxies of stars. Each flash was extraordinarily bright during that instant, sometimes outshining whole galaxies of stars. For a moment, the burst would dominate the sky's glow, as if billions of suns had flickered to life. To the satellites, each flash was like a cosmic lighthouse beam, briefly sweeping across the darkness, guiding weary cosmic travelers home before fading away again. Each flash had its own character. Scientists eventually noticed that there were roughly two types. Some bursts lasted longer, sometimes more than a minute, while others were over in less than 2 seconds. The longer bursts often exhibited a complex dance, with rising and falling intensity, as if the source was pulsating. The shorter ones were like a sudden flare, over almost as soon as it began. Despite these differences, the common thread was unmistakable. Every burst was intensely bright, by any cosmic measure. Each time a gamma-ray burst was detected, it presented its own story in light. The instruments recorded how the burst brightened and faded, second by second. Some bursts had a single smooth peak. Others danced with multiple spikes of light. Astronomers examined these light curves carefully, searching for clues. Each pattern seemed unique, like a fingerprint of the cataclysm that caused it. Bursts did not follow any schedule or calendar. They happened at all times, day or night. For the gamma-ray detectors, sunlight was irrelevant. They could observe the sky regardless of daylight. That meant they paid no attention to our concept of night sky. The cosmos could light up with a burst while it was daytime on Earth, and no eyes on the ground would even know unless they found the afterglow hours later. Tracking gamma-ray bursts was like playing catch with lightning. The bursts arrived without warning. Scientists had to spring into action immediately to gather all possible data. When a burst triggered detectors, they would scramble to point other telescopes in the right direction. Within minutes or hours, observatories around the world might be trained on the spot in the sky where the flash had come from, searching for any lingering light. It was a coordinated cosmic chase, all set in motion by that silent flash of gamma rays. Often, the gamma-ray burst left a fading trace called an afterglow. Telescopes detected a ghostly echo of the explosion in X-rays or visible light, minutes to days later. The afterglow revealed the burst's location more precisely and showed it dimming over time. Sometimes, astronomers even saw the birth of a bright new point of light, the exploding star's remnants emerge. These afterglows confirmed that each gamma flash was not just noise, it was the final act of an extraordinary event. To human senses, none of this would ever be noticeable, but in the instruments, the sky itself became a cinema. Each burst was a scene change, an unexpected flash of brilliance on a mostly black stage. Then the scene would drift back to darkness, waiting for the next burst to animate it. It was a silent, invisible film playing out across the cosmos, visible only to those who had built the right eyes. Because catching a burst was so fortuitous, teams felt like cosmic fishermen who had at last spotted a legendary fish in the dark ocean. When a burst occurred, the excitement was palpable. Instrument readouts would light up, showing the burst's fingerprint in real time. For a moment, scientists might gather around a console, watching lines on a graph spiking unexpectedly. It was proof that out there, beyond our solar system, something dramatic had just taken place. And then, just as suddenly, the instruments would go quiet again, leaving only the record behind. The bursts also held secrets in their timing. Astronomers measured the intervals between bursts to see if any regularity existed, but there was none. Sometimes bursts would come days apart, and then weeks would pass with none at all. It was completely random in time, as if the universe flipped a coin at unpredictable intervals. This lack of schedule made the bursts even more mysterious, as there was no way to predict where or when the next flash would appear. Each gamma-ray burst, in essence, was a lonely flash on the stage of the universe. Astronomers likened them to lighthouses, but with a catch. Unlike a familiar lighthouse on shore, these cosmic lighthouses only blinked once and then vanished. The only way to study them was to catch that one blink. Yet even in that brief moment, they left lasting marks. Radio telescopes sometimes heard the dying echo of a burst years later, proving that these flashes were signals from incredibly distant, exotic places. Imagine looking up on a starless night, expecting silence, when suddenly the heavens light up for a moment. That is the experience of the instruments searching for gamma bursts. They would catch a whisper of energy from a faraway flash, then watch it fade. These were cosmic beacons of an unseen storm, guiding astronomers to questions they had never asked. Because these flashes were so brief, It was only by chance that the satellites caught them at all. Many more bursts likely passed unnoticed, invisible to us, without our instruments ready at that moment. Each recorded burst was a gift of cosmic insight, a snapshot of an incredible event billions of light years away. With each new piece of data, the mystery grew. The way these bursts appeared in our detectors was intriguing, but just the beginning. Scientists were left with more questions, now that they had seen what the bursts looked like. Where in the sky were they coming from? To answer that, observers turned their eyes to the heavens. In the chapters ahead, we explore the map of these bursts across the sky and what it tells us about their origins. As the years went on, hundreds of gamma-ray bursts were recorded. Astronomers plotted their positions on the sky, looking for clues. They expected, perhaps, to find clusters or patterns. Maybe the bursts would trace the Milky Way, or point to some other known cosmic structure. But the resulting map was baffling. Astronomers compared the data to the familiar structure of the cosmos. Unlike stars, which form the glowing band of the Milky Way, or distant galaxies that cluster into filaments, the bursts did not follow any known pattern. They were like messages from all over, with no apparent preference. Each flash was a lamp lit in some distant corner of the universe. Instead of clustering along the band of our galaxy, or any familiar pattern, the bursts were scattered all over the sky, north, south, east, and west. They appeared everywhere. There was no favoured direction, no bias towards the plane of the Milky Way, no hint of any pattern at all. It seemed as if the entire heavens were sprinkled with these secret flashes. The uniform spread of bursts suggested a profound idea. Gamma-ray bursts come from far beyond our own galaxy. They were not fireworks happening locally. They were cosmic flares, lighting up the universe at immense distances. Each flash, faint by the time it reached us, started out as a cataclysm of unimaginable power somewhere in the distant cosmos. The isotropic, almost cosmic salt-like pattern was so unexpected that it demanded attention. If the sources were close by, or even in our own galaxy, there would almost certainly be some unevenness to their positions. Yet from our vantage point, every direction looked the same. It meant the bursts were happening in faraway galaxies, perhaps billions of light years away. They must be truly cosmological in scale, not nearby fireworks at all. This uniform sprinkling of bursts on the sky became the astronomers' most important clue. No other cosmic phenomenon had been so evenly spread. It told them that the universe was whispering secrets that could not be ignored. If these bursts came from all directions, then the cosmos itself was their stage, and Earth but a small spectator. To solve the mystery, scientists would need to consider the grandest scales of the universe. In the 1990s, instruments like NASA's Compton Gamma Ray Observatory, with its BATSI instrument, detected thousands of bursts and made detailed sky maps. The results were emphatic. Gamma-ray bursts were distributed uniformly. Astronomers even plotted the locations in galactic coordinates and saw no clustering towards the center or edges of the Milky Way. This confirmed definitively that these flashes must originate from outside our own galaxy. Think of it this way. If the bursts were fireworks set off within our galaxy, we would likely see more in the direction of the dense central bulge or spiral arms. But the bursts showed no favoritism. They were as likely to come from the sparsely populated regions of the Milky Way as from the crowded core. It was as if the universe was telling us, "You are looking at a phenomenon too grand to be constrained by our galaxy alone." The lack of any correlation made scientists take a step back. They compared the bursts to other cosmic maps: the Milky Way, the cosmic microwave background, clusters of galaxies, and found nothing matching. The bursts simply did not care about the cosmic structures we knew. In fact, the more bursts were recorded, the more uniformly they filled the sky. This pattern was itself a revelation. It confirmed that humans were not at the center of anything significant. These bursts were a universal phenomenon. One might compare this discovery to looking at a world map and finding the same number of cities in every country, big and small. It simply wouldn't make sense if cities were evenly spread across continents, just as it didn't make sense for cosmic explosions to be evenly spread across the sky. Gamma-ray bursts had effectively taught us a new geography, one where every direction was special. With that realization, the path was set. Gamma-ray bursts had earned their title as the universe's deadliest explosions, worthy of our deepest questions. Astronomers stood ready to explore those questions in the chapters ahead, knowing that each flash came from a distant, powerful event. The more bursts astronomers recorded, the more they realized how extraordinary these events were. Each flash, after traveling billions of light years, still carried more energy than anything humans could create. To put it in perspective, a single gamma-ray burst could outshine all the stars in the entire observable universe for a moment. Some bursts unleashed more energy in 10 seconds than our sun will emit over its entire 10 billion year lifetime. In fact, one observed burst released as much energy in 10 seconds as our sun emits over its entire 10 billion year lifetime. That meant one gamma-ray burst, for a brief cosmic moment, could outshine all other stars in its galaxy combined. It was truly a phenomenon on a galactic scale. Faced with these mind-boggling numbers, theorists began to spin scenarios. One idea was that gamma-ray bursts were the death cries of massive stars. We know that when a giant star runs out of fuel, it often goes out in a blaze known as a supernova. Some theorists thought that an especially massive star might collapse directly into a black hole, bypassing an ordinary supernova. In that violent collapse, energy could be focused into narrow jets that punch through the star's outer layers, firing gamma rays into space. This model imagined each long gamma-ray burst as a hypernova, a supernova marking a star's dramatic end. Another idea involved the union of two dead stellar corpses. If two neutron stars, city-sized spheres of nuclear density matter, spiraled into each other, the collision would be titanic. Such a merger could briefly create an even denser object, perhaps a black hole, and fling out energetic jets in the process. In essence, the combined kinetic energy of two orbiting dead stars could be released in one final burst of gamma rays. This idea was attractive because neutron stars do exist in binary systems and can collide due to gravitational waves. People noted that a collision like this might appear as a quick flash of gamma rays, possibly explaining short bursts. Magnetars were another intriguing possibility. These are rare neutron stars with extraordinarily strong magnetic fields, trillions of times stronger than Earth's. A magnetar can occasionally crack and shift violently, sending a wave of energy outward. On a smaller scale, magnetars had already been known to produce gamma-ray flares. Some scientists thought that an extreme flare from a magnetar in our galaxy could mimic a short gamma-ray burst if we were lucky enough to see it. However, the bursts being studied appeared much too powerful to come from any object inside the Milky Way. They were simply too luminous to be so near. Some scientists even considered more exotic explanations. Could these flashes be caused by the collapse of massive rings of debris, or by cosmic strings, theoretical objects from the early universe? One suggestion was that rare neutron stars, called magnetars, might have spectacular magnetic storms. We don't yet have all the answers, but each idea shared one thing in common: truly unimaginable power fueling these bursts. One particularly bold suggestion was that tiny primordial black holes left over from the Big Bang might occasionally evaporate in a final burst of radiation. If a black hole became small enough, Stephen Hawking showed it could release enormous energy as it disappears. A mini black hole evaporating could, in theory, produce a flash of gamma rays. This idea merged cosmology with gamma-ray astronomy, and even speculative physics found its way into the discussion. Meanwhile, some researchers looked closer to home for answers. Perhaps a previously unknown type of stellar object within the Milky Way could produce the bursts. For example, magnetogiant flares in our own galaxy, if violent enough, could mimic a short gamma-ray burst from afar. However, as more data accumulated, the evidence pointed toward faraway sources. No gamma-ray burst showed any sign of correlating with the plane of our galaxy, making a local source less likely. Still, considering these local possibilities helped rule out nearby origins and focused attention on the universe beyond. Of course, every model had to face reality. Astronomers knew that whatever caused the bursts, it had to fit the facts. The bursts were coming from great distances, must be extremely rare, and had to send out gamma rays in certain ways. Some ideas didn't survive scrutiny. For example, a local neutron star flare within our galaxy might sometimes appear similar to a real gamma-ray burst, but most detections showed the bursts were far too energetic. Others' theories faded as quickly as they appeared. Scientists realized that to truly understand these cosmic explosions, they needed more clues, like knowing how far away they were, what galaxies they lived in, and what stars, if any, accompanied them. The more bursts astronomers recorded, the more they realized how extraordinary these events were. Each flash, after traveling billions of light years, still carried more energy than anything humans could create. To put it in perspective, a single gamma-ray burst could outshine all the stars in the entire observable universe for a moment. Some bursts unleashed more energy in 10 seconds than our sun will emit over its entire 10 billion year lifetime. In fact, one observed burst released as much energy in 10 seconds as our sun emits over its entire 10 billion year lifetime. That meant one gamma-ray burst, for a brief cosmic moment, could outshine all other stars in its galaxy combined. It was truly a phenomenon on a galactic scale. Faced with these mind-boggling numbers, theorists began to spin scenarios. One idea was that gamma-ray bursts were the death cries of massive stars. We know that when a giant star runs out of fuel, it often goes out in a blaze known as a supernova. Some theorists thought that an especially massive star might collapse directly into a black hole, bypassing an ordinary supernova. In that violent collapse, energy could be focused into narrow jets that punch through the star's outer layers, firing gamma rays into space. This model imagined each long gamma-ray burst as a hypernova, a supernova, marking a star's dramatic end. Another idea involved the union of two dead stellar corpses. If two neutron stars, city-sized spheres of nuclear density matter, spiraled into each other, the collision would be titanic. Such a merger could briefly create an even denser object, perhaps a black hole, and fling out energetic jets in the process. In essence, the combined kinetic energy of two orbiting dead stars could be released in one final burst of gamma rays. This idea was attractive because neutron stars do exist in binary systems and can collide due to gravitational waves. People noted that a collision like this might appear as a quick flash of gamma rays, possibly explaining short bursts. Magnetars were another intriguing possibility. These are rare neutron stars with extraordinarily strong magnetic fields, trillions of times stronger than Earth's. A magnetar can occasionally crack and shift violently, sending a wave of energy outward. On a smaller scale, magnetars had already been known to produce gamma-ray flares. Some scientists thought that an extreme flare from a magnetar in our galaxy could mimic a short gamma-ray burst if we were lucky enough to see it. However, the bursts being studied appeared much too powerful to come from any object inside the Milky Way. They were simply too luminous to be so near. Some scientists even considered more exotic explanations. Could these flashes be caused by the collapse of massive rings of debris, or by cosmic strings, theoretical objects from the early universe? One suggestion was that rare neutron stars, called magnetars, might have spectacular magnetic storms. We don't yet have all the answers, but each idea shared one thing in common: truly unimaginable power fueling these bursts. One particularly bold suggestion was that tiny primordial black holes left over from the Big Bang might occasionally evaporate in a final burst of radiation. If a black hole became small enough, Stephen Hawking showed it could release enormous energy as it disappears. A mini black hole evaporating could, in theory, produce a flash of gamma rays. This idea merged cosmology with gamma-ray astronomy, and even speculative physics found its way into the discussion. Meanwhile, some researchers looked closer to home for answers. Perhaps a previously unknown type of stellar object within the Milky Way could produce the bursts. For example, magnetar giant flares in our own galaxy, if violent enough, could mimic a short gamma-ray burst from afar. However, as more data accumulated, the evidence pointed toward faraway sources. No gamma-ray burst showed any sign of correlating with the plane of our galaxy, making a local source less likely. Still, considering these local possibilities helped rule out nearby origins and focused attention on the universe beyond. Of course, every model had to face reality. Astronomers knew that whatever caused the bursts, it had to fit the facts. The bursts were coming from great distances, must be extremely rare, and had to send out gamma rays in certain ways. Some ideas didn't survive scrutiny. For example, a local neutron star flare within our galaxy might sometimes appear similar to a real gamma ray burst, but most detections showed the bursts were far too energetic. Others' theories faded as quickly as they appeared. Scientists realized that to truly understand these cosmic explosions, they needed more clues, like knowing how far away they were, what galaxies they lived in, and what stars, if any, accompanied them. Some scientists even speculated about phenomena at the very edge of known physics. One wild idea was that tiny, primordial black holes, left over from the Big Bang, might occasionally evaporate in a final burst of radiation. If a black hole became small enough, Stephen Hawking showed it could release enormous energy as it disappears. A mini black hole evaporating could, in theory, produce a flash of gamma rays. This suggestion merged cosmology with gamma-ray astronomy, bringing even speculative physics into the conversation. Meanwhile, others looked closer to home for answers. Some proposed that perhaps a known but rare type of object in our galaxy, if extraordinarily violent, could mimic these bursts. For example, a magnetar in our own galaxy, producing an exceptionally powerful flare. However, the more the scientists watched, the clearer it became that local sources couldn't account for all bursts. The key clue was that no gamma-ray burst showed any preference for the plane of our Milky Way. Over time, it became apparent that these were not local phenomena at all, but signals from the distant universe. Theories involving nearby objects lost favor as evidence piled up. The uniform sky distribution suggested that sources were spread throughout many galaxies. It was as if the entire cosmos was hosting these explosive events, and we were witnessing only a tiny piece of the grand show. Throughout the first decades of study, the first theories stood as guiding visions in the darkness. They gave context to the data, shaping how researchers thought about the next steps. It was still early days, and the universe had not yet revealed whether these ideas were correct. But one thing was clear. The story of gamma-ray bursts was only beginning. Humanity had glimpsed the scale and mystery of these explosions, and stood poised on the edge of understanding. The hidden fire in the sky had been revealed as a question written in light, and the quest to read it was just beginning. The life of a truly massive star is a tale of extremes and swift change. These giants form in dense stellar nurseries, often alongside many companions in tight clusters. In such crowded nurseries, interactions with neighbors can profoundly affect a star's fate. A star may be born with tens or even hundreds of times the mass of our sun, making it a beaming lighthouse in the night sky, but it will live only a few million years. From the moment it ignites, it is driven at a breakneck pace. Gravity compresses its core so intensely that it fuses hydrogen into helium and then rapidly into heavier elements, layer by layer like an onion. By the time it exhausts hydrogen, it has already built up a core of helium, which then fuses into carbon and oxygen, then neon, magnesium, silicon, and finally iron. Each new fusion stage proceeds more rapidly than the last. The final silicon burning phase may last only days or even hours. In all, this brilliant blaze of fusion might consume only a few million years, a mere heartbeat for stars of such size. Throughout this life, the star shines with stupendous power. It can burn billions of times brighter than the sun, its radiation driving fierce stellar winds. If the star forms in a metal-rich environment, like our Milky Way, those winds are especially strong, blasting away mass at rates of 1,000,000 times that of the sun's winds. These winds peel away the star's outer layers over its life. By middle age, it may have swollen into a red or yellow supergiant hundreds of times wider than the sun, or stayed compact and blue and fiercely hot if it was heavy enough. Either way, layers upon layers of fusion build in its interior, each shell burning a different fuel. Hydrogen burns in the core, then helium in a shell around it, then carbon, and so on, each outward shell adding complexity. To an observer, the star might seem steady and bright, but inside it is a ticking furnace running at the edge of what physics allows. An important factor in this evolution is the star's metallicity, the amount of elements heavier than helium it contains at birth. In galaxies with lots of heavy elements, these massive stars lose mass even more quickly and slow their spin. In early or small galaxies with low metallicity, stars can retain more of their mass and spin faster. Astronomers find that the long gamma-ray bursts we observe tend to come from metal-poor, star-forming galaxies. In other words, it often takes very rare conditions, a massive star born spinning like a top and not losing too much mass, to set the stage for a GRB. It's also common for massive stars to have companions. Many of the largest stars live in binary or multiple systems. A neighboring star can strip gas off its partner or even merge with it. Such dramatic interactions can spin up a star or strip its outer shell, revealing its hot core. For example, if two massive stars spiral together, they may ignite a new phase of burning or leave behind a rapidly spinning core. In effect, living among siblings can prepare a star for its final act. It might be left with a bare, helium-rich core and a rotation close to breakup speed. This naked, rapidly spinning core is an ideal progenitor for a long GRB. Although these stars live fast, they often die catastrophically faster. For the star burning through silicon and iron in its core, things come to a head. Iron fusion does not produce energy. Once the core is iron, further fusion actually consumes energy. Deep inside the core, even the iron nuclei can begin to fall apart under intense radiation, a process called photodisintegration, sapping the core's support. In a flash, the core's pressure gives way. What had been a stable, blazing sphere becomes a collapsing globe. In an instant, the core is crushed. Perhaps a region weighing more than our sun suddenly packing itself into a space the size of a city. From the outside, this collapse is hidden. To us, the massive star may still look like a bright point of light. Inside, it is a ticking bomb. You might picture it as a mountain carrying more and more snow. It looks stable until suddenly it avalanches, or like a pressure cooker set too high. Steam and heat build until the lid can't hold. Then comes the rapid core collapse. Gravity wins in a heartbeat, and the star's iron core implodes catastrophically. As it does, conditions become unbelievably extreme. Temperatures rise to billions of degrees, densities far beyond anything we experience. New particles and streams of neutrinos, ghostly neutrinos flooding outward, are produced. If the collapsing core is heavy enough, well over 3 solar masses in the core, it will form a black hole at its center. If somewhat lighter, it might form a neutron star. But in the scenario for long GRBs, we focus on black holes. Either way, the inner region is no longer a peaceful fusion reactor. It has become a violent engine. From that crushing darkness emerges an enormous burst of energy. A black hole, newly formed, acts like a cosmic engine. The outer layers of the star are still falling in, rather than plunging straight into the hole. Much of this infalling gas swirls into an accretion disk around the black hole, like water spiraling down a drain. This disk becomes searing hot, radiating X-rays and even gamma rays. The disk's turbulence and the black hole's rapid spin create intense magnetic fields. Imagine the disk and fields as a spinning dynamo. They tap the black hole's gravitational energy. In effect, the black hole's spin is converted into jets of power. One way to picture it is to think of an enormous flywheel spinning at tremendous speed. Magnetic field lines anchored in the hole and disk wind up like elastic bands and fling material outward. This magnetic dynamo process, often called the Blandford-Znayak mechanism by astrophysicists, channels energy into two narrow funnels along the hole's rotation axis. Within seconds, two jets of plasma shoot out from the poles of this newborn engine. They blast away from the black hole at nearly the speed of light. You can think of them as twin searchlights in the dark vacuum of space, each beam stuffed with exotic material. The jets consist of a hot plasma, electrons, positrons, photons, and possibly some atomic nuclei, racing out at relativistic speeds. These beams are extremely well collimated. Something has focused them into tight, narrow cones. The star's collapsing envelope and the twisted magnetic fields act together to keep the jets on course, preventing them from flaring outward too much. If Earth lies within one of these beams, we are in for the show. If not, we might see only a faint afterglow, or nothing at all. This tight collimation is crucial to producing the observed gamma-ray flash. What powers these jets to such amazing energies? There are a few ingredients. First, the gravitational potential of the black hole is enormous. As matter falls in, it releases energy. Second, the accretion disk is a torrid furnace of neutrinos. Neutrinos are subatomic particles that carry energy away from the disk. In this hyperdense core, neutrinos and their antiparticles annihilate, producing even more photons and electron-positron pairs. Although neutrinos usually pass through matter harmlessly, here so many are created that their annihilation can deposit significant energy along the poles, effectively adding fuel to the jets. Third, magnetic forces play a major role. The disk and black hole spin both twist-up magnetic field lines. These lines thread the black hole's event horizon and reach out into the surrounding space. As the black hole spins, it drags these lines like a Ferris wheel dragging spokes. This process can extract rotational energy from the hole itself. In practical terms, it's as if the black hole's spin were an enormous flywheel, and the magnetic field lines are belts pulling energy out to power the jets. This is one of the most efficient ways to launch the material at near light speed. All this energy, gravitational, neutrino-driven, magnetic, goes into the jets, but not all of it emerges as gamma rays. Inside the jets, the material moves in a complex dance. The central engine may spew material at varying speeds, so that faster blobs catch up with slower ones. When such collisions occur inside the jet, they produce shock fronts. It is these internal shocks that convert the bulk kinetic energy of the jet into high-energy photons. Imagine cars on a highway. A fast car slams into a slower one, and the crash releases a burst of light. Similarly, in the jet, particles accelerated by shocks emit gamma rays impulses. This produces the jagged, flickering profile of the burst that we detect. For an outsider, the jets are a point source on the sky. At this stage, the collapse itself is hidden by the star's material. We cannot see what is happening deep down, but all that energy is funneling into the jets. If we are lucky, one of those beams points nearly toward Earth. Then, after traversing the star, the jet will emerge into space, and the burst will be visible to us. Inside the star, however, the jets face a major obstacle: the star's own thick layers. For a brief, tense interval, the jets are trapped inside the collapsing star. They punch forward like drills, but they have to bore through perhaps 1,000,000 kilometers of stellar gas and plasma. Picture a powerful stream of water trying to cut through a block of ice. It takes time and force. As each jet head pushes outward, it drives gas sideways, heating it. A hot cocoon of plasma forms around the beam, filled with shocked stellar material and radiation. This cocoon actually helps chisel a tunnel through the star for several seconds, or longer if the star is very large. The jets and their cocoons creep outward. The rest of the star may not even realize what's happening inside. To an outside observer, the star's surface seems unchanged. Then comes the breakout. Suddenly, as if a trapdoor were thrown open, the leading edge of a jet punches through the star's surface. The transition is abrupt and brilliant. When the jet breaks free, a blinding flash erupts into space. First, there is often a burst of X-rays and gamma rays escaping out along that newly opened path. Simultaneously, the cocoon itself vents its hot contents, producing a burst of softer X-rays and ultraviolet light. In that instant, the veil of the star's envelope is torn away along the jet's narrow path. For a few heartbeat moments, the star itself seems to wake up to the catastrophe. Its outer layers are ripped apart. From Earth's vantage, this breakout is the birth of the gamma-ray burst. One moment, we were anticipating cosmic fireworks. The next, the night sky is flooded with the burst's light. The most energetic photons, the gamma rays, flood out first, marking the precise start of the GRB. To us, it looks like a sudden flash that outshines everything else in the universe. If we were aligned just right within the jet's narrow cone, we see every pulse. If slightly off axis, we might see a fainter signal, or only the afterglow that follows. Even as the jet blaze is being unleashed, the rest of the star is also exploding. The shock from the core collapse is sweeping through the star's remaining envelope. This drives a supernova explosion. The stellar material is lit up as it expands outward. In fact, days after the gamma-ray flash, clever astronomers will train their telescopes on that location and see a new point of light, the supernova. They are not looking at a newborn star, but at the death of the one we saw before. Over the following days and weeks, this supernova brightens and then fades, releasing energy primarily from the decay of heavy radioactive elements like nickel-56 created in the explosion. The link between the GRB and the supernova is striking. In every well-studied case of a long-duration GRB in our own cosmic neighborhood, astronomers have indeed seen a broad-lined Type 1c supernova in its wake. Type IC means the explosion's spectrum shows no hydrogen or helium, just heavier elements. That fits perfectly with our picture. By the end, the star had already shed its hydrogen envelope, leaving behind a core of carbon, oxygen, and heavier nuclei. The broad spectral lines mean the material is moving extremely fast, often tens of thousands of kilometers per second. These are unusually energetic explosions, so energetic that astronomers sometimes call them hypernovae. They can make a significant amount of radioactive nickel-56, powering the brilliant optical display. In some cases, the supernova peak brightness is so high that for a time it outshines a billion suns in its host galaxy. Yet it's important to remember how rare these events are. For every long GRB we observe, there are thousands of similar massive stars that exploded more quietly. Most core collapse supernovae do not produce a GRB that points at us. We only see the more common supernova without the gamma burst. Thus, long GRBs are like the celebrities of stellar deaths, flashy and rare, only stars that meet stringent conditions, extremely high mass, very fast spin, and an orientation that points one of the jets at Earth will give us this full fireworks show. Stars in metal-rich galaxies, where strong winds strip away mass, seldom meet these conditions, so instead we find long GRBs in small, young, metal-poor galaxies bursting with star formation. After the initial flash of gamma rays and the burst of supernova light, the story continues in softer wavelengths. In the quiet aftermath of the burst, the drama is far from over. The jets, now free of the star, slam into the gas and dust that surrounds the stellar remnants. This collision sets up powerful shockwaves in the interstellar medium. Within minutes, the shocked gas is so hot that it emits X-rays. Space telescopes begin to detect an afterglow of X-rays coming from the burst location. This X-ray afterglow is usually bright at first, then gradually fades as the blast wave expands and loses energy. At the same time, the shocked gas also emits ultraviolet light for a short time, which then transitions into visible light as it cools. From a few hours to days after the burst, Sensitive optical telescopes on Earth find a glowing point of light where the GRB occurred. This afterglow in visible light can be remarkably bright, sometimes briefly rivaling the brightness of a nearby bright star. But then it dims steadily over time. Astronomers monitor this fading beacon night after night. The afterglow typically fades roughly following a power law, growing fainter by perhaps an order of magnitude every few days. Because the light curve and spectrum of the afterglow follow predictable physics, it can often be observed long enough for scientists to take spectra. These spectra let them measure the redshift, that is, the distance to the burst's host galaxy, and probe the material between us and the source. In fact, many gamma-ray burst afterglows reveal absorption lines from the gas and dust in the host galaxy, telling us about its composition and distance. Even longer after the initial flash, radio telescopes pick up the fading echo. A week or more later, observers might point a radio array at the site and find a faint radio source. This radio afterglow typically rises and falls over weeks or months. It arises from the same shockwave, now slowed and ploughing into more distant gas. At these longer wavelengths, the afterglow can sometimes be seen for months or even years before it disappears. By measuring the radio emission, astronomers can estimate how much energy the explosion had and how dense the surrounding medium is. It's like tracking the ripples of a pond long after the stone was thrown. Across this entire afterglow, from X-ray to ultraviolet to optical to infrared and then radio, a clear picture emerges. The collisions in the blast wave accelerate electrons to near light speeds. These electrons spiral along magnetic fields created in the shocks, emitting synchrotron radiation at all these wavelengths. In effect, the single explosive event spawns a fading light show that gradually sweeps through the spectrum. Early on, we see high-energy X-rays. By day, we see optical light. By week, we see radio waves. For months, the ghosts of this cosmic explosion linger, allowing astronomers to dissect the environment around the star and the physics of the blast. This lingering afterglow is the dying star's final tale. Each wavelength carries a piece of the story, revealing details about how fast the jets were, how energetic the blast was, and what the surroundings were like. Over days and weeks, the echoes slowly fade into the cosmic night. Even as they dim, they have told us the secrets of one of the universe's mightiest explosions. The universe has witnessed a supernova of epic proportions, one of its deadliest fireworks shows, and through the fading light left behind, its story remains written across the cosmos. Beyond the blazing lives of stars, there is a quieter realm of stellar afterlives. Instead of witnessing a single star's final blaze, we now observe the quiet dance of two stellar remnants. Here, two neutron stars, the dense corpses of past supernovae, orbit each other in silence. In this celestial dance, time is measured by the eternal gravitational tug between them. Over eons, they spiral gradually closer, locked in a final embrace, destined to end with a burst of unimaginable power. These are stellar corpses, compressed into city-sized spheres, heavier than our sun, yet compact enough to fit on Earth's horizon. These twin remnants are not common. In the Milky Way, perhaps only a handful of neutron star pairs are destined to collide within a few billion years. However, the cosmos is vast. Even rare events become common when you consider the countless galaxies in the universe. So while such binaries are scarce locally, across the cosmos, there may be many happening at any given time. In their birth, these neutron stars were forged in cataclysmic supernova explosions. They pack the mass of a star into a sphere only tens of kilometers across. A teaspoon of their material would weigh 1 billion tons. This unimaginable density means their gravity is extreme, bending light and warping space around them. Yet despite this intense nature, out here, they dance with quiet grace. Inside such stars, atoms are so squeezed that electrons are forced into nuclei, creating a sea of neutrons, essentially a single gigantic atomic nucleus. At these pressures, matter behaves in ways we have only begun to explore. For many neutron stars, companionship is part of fate. If two massive stars were born together in a binary, both might end their lives as neutron stars. When both stars collapse, they become locked in a silent cosmic waltz, each orbiting the other under the strict pull of gravity. Often, one of these stars remains active as a pulsar, a rapidly spinning neutron star that sweeps beams of light or radio waves across space like a lighthouse. When its beam flashes past Earth, astronomers receive a steady pulse of energy. By timing these pulses with extraordinary precision, scientists can map the star's orbits in great detail. Over years of monitoring, researchers have seen these pulsar beacons of binary systems changing subtly. In 1974, the first such system was discovered, and its orbital period slowly decreased over time. This was exactly what Einstein's theory predicted would happen if the pair were losing energy as gravitational waves. In effect, the star's orbit tightened like a clock wound down by the emission of space-time ripples. This discovery confirmed that neutron star binaries do emit gravitational waves, and that their orbital decay matches theoretical predictions. It was a landmark proof that the cosmic dance of these dead stars follows the same physics of relativity. For the dancing stars, time continues its slow march. As eons pass, their orbit keeps decaying, and their cycles quicken. At first, each orbit may take minutes or even hours, but as they draw closer, each cycle becomes faster and faster. In the final seconds, they spin around each other dozens or even hundreds of times per second. Eventually, these dense spheres draw so near that gravity pulls them into a final, fatal embrace. When they collide, the energy released can outshine entire galaxies for a brief instant. In this dramatic crescendo, the dance becomes a brilliant, powerful burst in the cosmic symphony. What remains after the collision? In most cases, the two neutron stars collapse into one object that may briefly resist gravity. If their combined mass is too great, a new black hole is born, consuming most of the mass. In some scenarios, the merged core might temporarily form an extremely massive neutron star, perhaps a magnetar, which could survive for seconds or minutes before collapsing. This newborn object, black hole or hypermassive neutron star, launches the jets that produce the gamma-ray flash. The nature of this remnant influences the details of the kilonova as well, such as its brightness and how quickly it fades. From our perspective, the finale happens in an instant. These stars can orbit in silence for millions of years, imperceptibly spiraling closer together. Only in the final moments does the dance snap into haste. In a single cosmic heartbeat, the stars collide, unleashing an explosion that marks the end of their long journey. These mergers ignite the universe's most fleeting fireworks, short gamma-ray bursts, releasing immense energy in just a heartbeat. This dramatic explosion is the universe's grand finale to the pair's long waltz. These collisions need not happen amidst dense star fields. A supernova explosion can kick the neutron stars away from their home cluster, sending them on lonely paths. By the time of collision, the pair may be wandering in the outskirts of a galaxy, or even in the quiet void between galaxies. In such cases, their final embrace might light up a place where previously nothing stirred. Astronomers have observed cases where a kilonova glows far from any visible galaxy, a lone fire in the cosmic night. In 2017, astronomers finally witnessed exactly such a collision. Detectors on Earth sensed the faint gravitational chirp of two neutron stars merging in a galaxy about 130 million light-years away. 2 seconds later, space telescopes recorded a flash of high-energy gamma rays from the same event. It was a breathtaking confirmation that even across vast cosmic distances, the echoes of these dead stars can reach us. That single observation united the tale we have been telling. Two stellar corpses spiraling together, their final embrace lighting up the universe in gravity and light. In fact, this observation was a direct confirmation of Einstein's century-old prediction. Einstein predicted gravitational waves in 1916, but for decades, they remained a theoretical concept. Many physicists wondered if we would ever be able to detect them. All of that changed in 2015, when the LIGO Observatory recorded the first direct evidence of gravitational waves from colliding black holes. That watershed moment opened a new window on the universe. From that point on, we could finally hear the cosmos as well as see it. Einstein's theory of gravity teaches us that space and time form a unified fabric. When massive objects move violently, they send ripples through this fabric, like waves on a pond. These ripples are gravitational waves, and they propagate outward at the speed of light, alternately stretching and squeezing space as they pass. But they are extraordinarily subtle. Only the most cataclysmic events in the universe can produce waves strong enough for us to notice. When two neutron stars collide in their final crash, they set space itself quivering with immense power. By the time such waves reach Earth, the effect is tiny, smaller than an atom's nucleus. We have built extremely sensitive detectors to catch those faint tremors and listen to the universe's gravitational symphony. It was only recently, in 2015, that instruments finally detected gravitational waves for the first time. Two merging black holes, far across the universe, sent out a brief burst of waves that the LIGO detectors picked up. Those black hole events taught us that gravitational waves are real, but they produced no light or gamma rays. The first time scientists heard the gravitational chirp of two merging neutron stars came in August 2017. LIGO and Virgo detectors caught the signal, a rising tone that began at low frequency and swept upward for nearly 100 seconds as the stars raced together. It was as if the collision played a note that climbed steadily, like a violinist drawing a bow faster and faster across the strings. By the final moments, the frequency of that gravitational signal had climbed to over 1,000 cycles per second. A true cosmic chirp. Scientists even call it a chirp, because its frequency rises like a bird's song. Imagine watching a thunderstorm. First you see a flash of lightning, then you hear the rumble of thunder a moment later. Lightning and thunder tell you the same story of the storm, separated by the speed of sound. In a neutron-star collision, the lightning is a flash of gamma rays, and the thunder is gravitational waves. But in space, both travel at the cosmic speed limit. When the stars collide, we see the flash and hear the rumble almost together. Two parts of the same cosmic event arriving in unison. When that gentle gravitational chirp ended, something amazing happened. Just 2 seconds later, space telescopes recorded a short flash of high-energy gamma rays from the same region of the sky. This brief burst of light had all the hallmarks of a short gamma-ray burst. The timing was unmistakable. The gravitational waves and the gamma flash came from the same cosmic collision. Together, they became movements of a cosmic symphony, gravity playing one instrument and light another. Satellites like NASA's Fermi telescope and the European Space Agency's Integral Observatory were watching the sky at that moment, and they caught the flash. It was as if the universe had announced, "Behold, this is the full story." In one stroke, astronomers confirmed that merging neutron stars indeed produce these brilliant, fleeting explosions. It was a historic moment in astronomy. Apart from confirming the origin of short gamma-ray bursts, the dual detection taught us something fundamental. Both the gravitational waves and the light arrived almost together, just 2 seconds apart after traveling 130 million light-years. This meant they were moving at the same ultimate speed, just as Einstein's theory predicts. In fact, this tiny delay over such a vast distance confirmed that gravitational waves travel at essentially the speed of light. It also nailed down the nature of the colliding bodies. The gravitational data showed the masses were those of neutron stars, and the presence of light told us they could not have been black holes, which would have left no light behind. In that way, gravity and light joined forces to reveal the true culprits of this cosmic event. Gamma rays are a form of light, the most energetic form in the electromagnetic spectrum. Each gamma photon can carry 1,000,000 times more energy than a visible light photon. We cannot see gamma rays with our eyes, and Earth's atmosphere blocks them. Instead, we rely on space telescopes to capture these bursts of energy. In a neutron-star collision, physicists believe the merger launches narrow jets that blast gamma rays out at near light speed. If one of these jets points toward Earth, we see a short, intense flash, the cosmic equivalent of a pinpoint flashlight turning on for an instant. These short bursts last under 2 seconds, yet they can unleash tremendous power. One such burst can emit more energy in that moment than our sun will produce in its entire 10 billion year lifetime. In practical astronomy, these observations launched the era of multi-messenger astronomy. For the first time, we had 2 completely different messengers telling the same story. Scientists call this multi-messenger astronomy. Using light, gravitational waves, and even neutrinos to study cosmic events in concert. Each messenger brings its own information. By listening to the universe with multiple senses, we can piece together a fuller picture of these powerful phenomena. From thousands of years of using only our eyes to now adding new ears tuned to gravity, our understanding of the cosmos has leaped forward. In the aftermath of these violent events, the cosmos still has more to show us. The initial storm of gravitational waves and gamma rays gives way to a softer glow. This fading light, known as a kilonova, marks the final act of the stellar collision. It is the universe's way of catching its breath and slowly revealing the secrets of what just happened. In that soft glow lie clues to the universe's alchemy, the forging of new elements in this violent union. We will now turn our attention to these glowing embers of the collision. The idea of a kilonova is not new. Decades ago, theorists predicted that the merger of neutron stars would produce a brief, bright afterglow. They coined the term kilonova because it would shine about 1,000 times brighter than a normal nova. The event of 2017 provided the first direct confirmation of this decades-old prediction. It was a triumph of theory and observation working together, a cosmic prophecy fulfilled. In the aftermath of the collision, the debris itself begins to glow. This is the kilonova, an afterglow of radioactive energy spreading through space. The debris from the collision is the perfect environment to forge heavy nuclei. In the first seconds after the crash, a furious burst of nuclear reactions takes place, a rapid neutron capture known as the R process. The result is a mix of radioactive isotopes. As these unstable elements decay, they heat the expanding debris and make it glow. In essence, the kilonova's light is powered by the radioactivity of freshly made heavy elements. The kilonova's glow is not a constant color. In fact, as the ejector expands and cools, its hue can shift. Some collisions produce an initial flash of blue light, lasting for a day or so, followed by a longer-lasting red-orange glow. This change in color happens because different elements have different opacities. The very heaviest elements, like the lanthanides and actinides, including gold and platinum, absorb light and re-radiate it in redder wavelengths. So as time passes, the kilonova often evolves from a bright blue to a dim red glow. Astronomers finally caught one of these kilonovae in action in 2017. After the gravitational wave and gamma signals from GW 170817, observatories around the world quickly turned to the source. Within hours, a new point of light was found in a distant galaxy, the expected kilonova. Over the next days, telescopes tracked this afterglow as it faded and changed color, just as models had predicted. This observation confirmed that neutron star collisions do indeed leave behind a glowing ember of radioactive debris. Finding that kilonova in 2017 was a true team effort. Once gravitational waves pointed astronomers to a patch of sky, dozens of telescopes around the world sprang into action. Within hours, a team using a small telescope in Chile identified the new point of light in the galaxy NGC 4993. Telescopes in South Africa, Hawaii, and elsewhere joined in, watching the afterglow fade and taking spectra to reveal its composition. It was the combined effort of many observatories that captured this transient glow and unlocked its secrets. Astronomers had also seen hints of kilonovae before the 2017 event. In 2013, after a short gamma-ray burst, observers noticed a faint infrared glow that didn't fit a normal afterglow. This was interpreted as a kilonova, a sign that a merger had occurred, even without gravitational wave data. Such clues had suggested these events were happening, even if they were hard to catch. The 2017 kilonova was the first time we could verify those suspicions with full multi-messenger confirmation. Future telescopes will make this field even richer. The James Webb Space Telescope, for example, is equipped to observe the infrared glow of distant kilonovae that current instruments might miss. With its powerful cameras, JWST could detect kilonovae in faraway galaxies or even in the early universe. Each new observation will refine our models of these explosions and their aftermath. The study of kilonovae is just beginning. Upcoming astronomical surveys are expected to find these afterglows in large numbers. For example, the Vera Rubin Observatory, LSST, will repeatedly image the sky and could spot many kilonovae each year, even without a gravitational wave trigger. Astronomers are also building dedicated follow-up networks to rapidly study any new transient. In the coming decade, we expect dozens or even hundreds of kilonova detections, each one adding to our understanding of these cosmic embers. In a deeper sense, kilonovae are natural laboratories for extreme physics. The conditions in the ejected debris, immense neutron density and rapid expansion, are unlike anything on Earth. By observing how the kilonova brightens and fades, astronomers can test their models of nuclear physics. The data inform us about how atomic nuclei form and decay under these exotic conditions. Each kilonova thus teaches us not only about astronomy, but about the fundamental building blocks of matter. Not all kilonovae are equally bright. The exact brightness depends on details of the merger. If one neutron star is much larger than the other, it may be swallowed with minimal debris, producing only a faint afterglow. Similarly, if the collision yields fewer neutrons, the resulting glow will be weaker. Astronomers use models to predict the expected brightness based on these factors and compare them to observations. In practice, we usually find kilonovae after a trigger. When a short gamma-ray burst or gravitational wave alert points us to a likely merger, we target that area of the sky. Looking blindly, a kilonova could easily be mistaken for other transient events, like supernovae or exotic flares. By connecting the glow to a known merger, astronomers can be confident they are observing the correct afterglow. In these glowing embers, we glimpse the cosmic alchemy at work. The kilonova is more than just a light show. It is the visible signature of the elements created in the merger. By studying kilonovae, astronomers piece together the history of matter forged in the hearts of dying stars. Soon we delve deeper into this alchemy, seeing how neutron star collisions forge gold, platinum, and more heavy elements. Our journey into these cosmic wonders continues on. In contrast, black hole collisions are like earthquakes in space. When two black holes merge, the event is enormously powerful, but entirely invisible to light-based telescopes. These cosmic quakes register only in the fabric of spacetime. Since 2015, LIGO and Virgo have detected dozens of such mergers. Each came with a characteristic gravitational chirp, but no flash of light. In these cases, our only clue is the faint rippling tremor through the universe. It wasn't a complete surprise. Astronomers expected that black holes could form pairs and eventually collide. When two massive stars form together in a binary, both can collapse into black holes. These black hole binaries then wander the cosmos in silence, until eventually they too spiral together. The first gravitational waves ever detected, in 2015, came from such a binary black hole merger. These events have since become fairly routine in our instruments, each one alerting us only by gravity's whisper. Each new black hole merger reveals something new about these cosmic giants. The first gravitational wave detection, in 2015, involved two black holes roughly 30 times the Sun's mass, much heavier than any known before. This surprising discovery showed that there are binary black holes much larger than we had expected. Later detections have ranged from around 5 up to nearly 100 solar masses. These observations are teaching us about the life cycles of massive stars and how black holes can form in pairs. How do two black holes end up in a close dance? Astronomers have proposed a couple of paths. One is that two massive stars born together each collapsed into black holes, remaining a bound binary. Alternatively, in dense star clusters, lone black holes can pair up through gravitational interactions. The newly formed binary then loses energy through gravitational waves until finally merging. Each detected merger helps scientists understand which scenario is more common in the universe. The gravitational waves themselves reveal the properties of the black holes. By analyzing the waveform, scientists determine the masses and spins of the merging holes. This, in turn, hints at their history. For example, black holes that are spinning in the same direction might have evolved together from two stars, while misaligned spins might suggest a more exotic origin. Each black hole merger thus carries clues about how it was born and how it evolved. Under some unusual conditions, even merging black holes could produce light. For example, if the merger happened inside a gaseous disk of a supermassive black hole, models predict a flash of light might occur. In 2017, one merger detected by LIGO was tentatively associated with a faint gamma-ray signal by a NASA telescope. If true, this could be the first hint that black hole mergers might sometimes have an electromagnetic counterpart. However, this interpretation is uncertain and remains a topic of ongoing research. Some partnerships involve one of each, a black hole with a neutron star. In those cases, the outcome can vary greatly. If the black hole is massive, it may swallow the neutron star whole, leaving no debris to emit light. If instead the black hole is smaller or spinning fast, it can shred the neutron star before swallowing. In that case, some neutron star matter can escape, potentially producing a flash of gamma rays or a kilonova glow. Thus, a black hole neutron star merger can end either in near silence or with a burst of light. In fact, the first confirmed detections of black hole neutron star mergers came just recently. LIGO and Virgo picked up two such events in 2020. Analysis suggests that in both cases, the black hole was massive enough to swallow the neutron star whole. These mergers produced gravitational waves, but no burst of gamma rays was observed. It seems the cosmic cloak of the black hole swallowed even the light. Astronomers now know that if the circumstances are right, such a merger might still put on a show. But these early examples were quiet. Detecting these cosmic earthquakes is incredibly challenging. LIGO's instruments are so sensitive that passing trucks or ground motion can create signals in the data. To confirm a true black hole merger, multiple detectors must see the same pattern with the exact time delay expected. This coincidence filtering is how scientists separate real events from mundane vibrations. The successful detection of dozens of black hole mergers speaks to both their power and our technological prowess. Each black hole collision is also a test of fundamental physics. The shape of the gravitational wave signal matches Einstein's general theory of relativity to an extraordinary precision. Even in these most extreme conditions, near the point of no return of a black hole, no deviations have been found. In that sense, every detection confirms that our understanding of gravity is holding up under the universe's toughest conditions. These silent mergers are thus not just cosmic events, but experiments in spacetime itself. In the coming years, gravitational wave observatories will become even more sensitive, as detectors like Kagra in Japan and upgrades to LIGO/Virgo come online. We will hear more of these mergers, including those involving black holes and neutron stars. Each new detection could bring surprises, perhaps a BH-NS collision with an unexpected flare, or even the first merger of intermediate mass black holes. The cosmic orchestra of compact objects is far from fully composed, and we are eager to listen for every new note. One advantage of studying gravity waves is that they pass through any obstacle unimpeded. If a black hole merger takes place behind thick clouds of gas or far away in the universe, the space-time ripples still reach us. In other words, gravitational waves give us a clear view even when light is blocked. This makes them a powerful tool for exploring regions of space that are hidden in visible wavelengths. In the cosmic symphony, gravity carries every note across the universe without interference. Regardless of whether we see light, these compact mergers enrich our understanding of gravity and matter. The material involved in these dances, whether quietly consumed or violently expelled, carries the seeds of the universe's heaviest elements. These processes help create the ingredients that will one day become part of planets, asteroids, and even living creatures. Our exploration now turns to the cosmic alchemy at play in these collisions, as we examine how neutron star mergers forge gold, platinum, and more. In the story of element formation, neutron star mergers provide a crucial chapter. Regular stars can fuse elements only up to iron in their cores. Beyond that, fusion would consume energy rather than produce it. To build heavier nuclei, we need a torrent of neutrons, and neutron star collisions deliver that torrent. These collisions are, in fact, the best environments known for creating the universe's precious heavy elements. The fierce collisions we have described are also nature's ultimate foundries. In the wreckage of merging neutron stars, new elements are born. These events provide the perfect conditions for creating the heaviest elements in the periodic table. Decades ago, physicists predicted that neutron star mergers could solve the mystery of where gold, platinum, and similar elements come from. Those predictions have now been confirmed by observation. Astronomers had long suspected that merging neutron stars were responsible for the heaviest elements in the universe. For many years, the origin of elements like gold and platinum was a mystery. Supernova explosions alone could not account for enough of them. The collisions of neutron stars provided the missing piece. After the 2017 merger, telescopes observed telltale signs of newly created elements. In 2019, scientists even identified strontium lines in the kilonova's light, the first direct evidence of rapid neutron capture, nucleosynthesis. This confirmed that these explosive unions truly forge heavy atoms. During the merger, extraordinary numbers of neutrons become available. Seed nuclei quickly snatch up neutrons in a furious burst of building new elements. This rapid neutron capture, the R process, pushes nuclei up the periodic table to the heaviest elements. In effect, the debris is like a cosmic blender, mixing protons and neutrons into gold, platinum, uranium, and more. The result is a bounty of heavy nuclei. Scientists estimate that one merger could produce enough gold to fill the Earth's oceans if spread thinly. These newly minted atoms then decay into stable forms, but their radioactive decay is what powered the kilonova glow we observe. Each neutron star merger sends its newly forged elements out into the galaxy. Over time, these heavy atoms mix into gas clouds that form new stars and planets. In that sense, the gold in a wedding band or the platinum in electronics may once have been stardust from a neutron star collision. Our own bodies include elements like iodine and molybdenum that likely originated in these violent events. By unlocking how these collisions create elements, we trace part of our own heritage back to the distant cosmos. Astronomers have even found clues of ancient mergers in old stars. Some metal-poor stars in our galaxy show unusually high levels of heavy elements, a pattern that is best explained if a neutron star merger had already polluted the gas long ago. In this way, the fingerprints of these collisions appear in stars and planets billions of years later. The evidence is growing that these explosions have truly shaped the composition of our galaxy. To get an idea of the scale, consider this. A single neutron star collision might eject around 0.05 times the mass of our Sun in heavy elements. That amount of material contains on the order of 10 to the 53rd power atoms, many of them gold, platinum, and uranium. In human terms, that's enough gold to cover the entire Earth's surface in a layer several centimeters thick. Each of these events is a cosmic treasure chest opened onto the galaxy. In the grand scheme, each element in our bodies carries the legacy of these collisions: the iodine in our thyroid, the iron in our blood, even some of the uranium in our soil. All were forged in distant kilonovae long ago. When you hold a piece of gold or glance at a platinum object, remember that those atoms were once part of a neutron star's debris. In that sense, our very existence is intertwined with these cosmic explosions. There is even a chance that one of these ancient explosions helped shape our own solar system. Scientists speculate that a neutron star merger may have occurred in our galactic neighborhood just before the Sun formed. Such an event would have injected heavy elements into the cloud of gas that became our solar system. This could explain the particular mix of elements we see on Earth today. Though still speculative, this idea underscores how profoundly these cosmic collisions can influence star systems and planets. Each kilonova provides rich information for astronomers. By measuring its brightness and how quickly it fades, scientists can estimate how much material was ejected in the merger. The color of the light hints at the composition of the debris. In effect, every kilonova becomes a laboratory for studying nuclear physics under extreme conditions. Observers now eagerly scan the sky for these telltale glows whenever a neutron star merger is detected by other means. The kilonova's light tells us the story of the elements forged in that explosion. This deep exploration of stellar alchemy still has many chapters unwritten. Each neutron star collision we observe adds another stanza to the universe's grand poem, reminding us that there are always more secrets to uncover. With each heavy element, we trace back to its fiery origin. Our appreciation for the cosmos deepens, and so our journey continues onward, ever eager to see what wonders lie around the next corner of the universe. High above the Earth, far beyond the comfort of air and cloud, instruments wait in silence. They orbit in the vacuum, their gaze fixed outward, because the atmosphere below them is both protector and barrier. The very shield that keeps us safe from the most dangerous cosmic rays also hides them from our eyes. Gamma rays, the highest energy form of light, are stopped completely by air. No matter how large a telescope we build on the ground, not a single photon of gamma light will reach its mirrors. For centuries, humanity had no idea such storms even existed, because they were smothered before reaching us. To sense them, we had to leave the Earth behind and place our detectors in the emptiness above the sky. It may seem counterintuitive that our greatest discoveries about the universe's deadliest explosions depend on some of the most delicate instruments. These devices are fragile, their sensors and electronics carefully crafted to detect the faintest spark of energy from billions of light years away. A single burst can arrive without warning, flood a detector with photons, and vanish in an instant. The instruments must be always awake, their electronic ears open, waiting for a note in the silent cosmic song. From their orbits, they watch constantly, circling the Earth again and again, recording every flicker of unseen light. They have become our surrogate senses, showing us what we could never glimpse with our own eyes. The first attempts at gamma-ray astronomy were simple, piggybacking on satellites not designed for the task. Detectors meant to watch for nuclear tests were the first to discover cosmic flashes, as we've already seen. Those early instruments were crude, with poor resolution and limited memory, yet they revealed something startling. The sky was alive with unseen lightning. That revelation led to more ambitious missions, each generation of instruments becoming sharper, faster, and more sensitive. By the end of the 20th century, dedicated gamma-ray observatories orbited our planet, finally able to study these mysterious bursts in detail. The lessons they brought down would transform our picture of the universe. Each instrument designed for this task had to face challenges unique to space. Above Earth, satellites are battered by radiation from the sun and cosmic rays. Their detectors are delicate, easily confused by background noise or energetic particles that sneak past shielding. Scientists learn to distinguish the faint whispers of true gamma-ray bursts from the constant hiss of false alarms. They refined their sensors, improved their software, and developed rapid alert systems that could send messages to astronomers on the ground within seconds of a burst. Through these innovations, the watchtowers of space grew more capable, preparing us to catch the most fleeting cosmic fireworks. One of the most celebrated missions is a satellite called SWIFT. Its very name captures its purpose: to react quickly to sudden bursts of light. Launched in 2004, it carried a suite of instruments designed to catch gamma rays, then immediately swing around to study the afterglow in X-rays, ultraviolet, and visible light. For the first time, a single observatory could capture the full life of a burst from the first instant to the fading embers. SWIFT became a tireless sentinel, recording hundreds of bursts and sending instant alerts to telescopes on Earth. Each alert set off a chain of observations, a global chase after light that had traveled billions of years to reach us. SWIFT was soon joined by another sentinel, the Fermi Gamma-Ray Space Telescope, launched in 2008. Fermi broadened our view, with a wide-angle monitor capable of scanning the entire sky every 3 hours. Its sensitive detectors could capture gamma rays with energies higher than any seen before. Some bursts it observed emitted photons so powerful they challenged theories about how light could travel through space without scattering. Fermi revealed that bursts were not only frequent, but also staggeringly diverse, each with its own fingerprint. Together, SWIFT and Fermi created a golden era of gamma-ray astronomy, complementing each other's strengths and sharing discoveries with the entire scientific world. Whenever a burst was detected, a race began. The satellites could send signals to Earth in mere seconds, notifying observatories across continents. Robotic telescopes would pivot automatically, racing to catch the afterglow before it faded. Astronomers at larger observatories would follow, measuring the spectrum of the light to determine distance and composition. In the early days, this coordination was difficult, relying on human phone calls and manual alerts, but with time, an automatic network grew, a digital nervous system linking space telescopes and ground observatories. Today, a burst detected in orbit can trigger a cascade of responses worldwide, with telescopes of every size participating in the chase. The urgency is real, because these events are ephemeral. A gamma-ray burst itself may last less than a second or a few minutes. Its afterglow can fade within hours. To catch it, astronomers must move quickly, coordinating across time zones and continents. At observatories in the desert, in mountain ranges, and on remote islands, astronomers wake in the night to respond to these alerts. The bursts do not wait. They blaze and vanish, indifferent to our efforts. Yet again and again, the network succeeds, and the light is captured before it slips away. This race against time has become one of the most thrilling pursuits in modern astronomy. Through these coordinated campaigns, bursts are not only observed, but also placed on the map of the cosmos. Astronomers plot their afterglows against images of galaxies, identifying their hosts. Some bursts originate in tiny, faint dwarf galaxies, bursting with young stars. Others come from massive spirals, tucked into the arms where stars are born. Occasionally, a burst flares in a galaxy billions of light-years away, near the dawn of time itself. Mapping these bursts has shown us that they are truly cosmological, stretching across the history of the universe. Each plotted point is a reminder that explosions beyond imagination have happened in countless places and times. As the maps grew richer, patterns began to emerge. Long bursts clustered with regions of active star formation, where massive stars lived and died quickly. Short bursts were scattered more widely, often found in older galaxies, where neutron stars might have drifted for billions of years before colliding. These associations provided crucial evidence linking bursts to their origins, confirming theories that had been debated for decades. Each map added another piece to the puzzle, showing not just where the bursts occurred, but also what kind of environments produced them. In this way, the cartography of gamma rays expanded our knowledge of stellar life and death. But even with these successes, the universe continued to surprise us. Some bursts refused to fit neatly into categories. A few long bursts showed no supernova afterglow, defying the usual pattern of dying massive stars. Some short bursts were strangely bright, lasting longer than expected. Others produced flares and re-brightenings days later, as if their engines sputtered back to life. Each anomaly forced astronomers to reconsider their models, to accept that the cosmos often resists our tidy classifications. These unusual bursts are not nuisances, but gifts, offering fresh clues about the variety of processes that can unleash gamma rays. Among the surprises was the discovery of ultra-long bursts, lasting thousands of seconds. These events may come from stars, unlike any we had considered, perhaps blue supergiants with vast envelopes of hydrogen. Their slow collapse and prolonged jets might explain the extended flashes of gamma light. Another oddity appeared in bursts, with high-energy photons arriving seconds or minutes later than lower-energy ones, hinting at complex physics in the jet, or even subtle effects of spacetime itself. Such mysteries remind us that each burst is not only an explosion, but also an experiment, conducted by nature at scales we cannot replicate on Earth. Some bursts even hinted at connections to phenomena we had not imagined. A few seemed to coincide with flares from magnetars in our galaxy, suggesting that not all gamma flashes come from distant sources. Others raised the possibility of new physics, like violations of long-held principles of relativity. While most such anomalies eventually find explanations within known science, they keep astronomers alert, aware that the universe may still hold deeper surprises. Each surprising burst expands our horizons, reminding us that discovery often lies at the edges of expectation. The constant monitoring of the sky ensures that no storm goes unnoticed. With each passing year, new instruments are proposed and launched, each promising sharper eyes and faster responses. The story of observing gamma-ray bursts is still unfolding, as technology advances and global networks grow more seamless. What began with accidental discoveries has become a disciplined, worldwide collaboration, linking satellites, observatories, and data centers into a single web. Together, they listen for the faint whispers of the universe's most violent storms. And with every captured burst, the map of the cosmos becomes richer, guiding us deeper into the mystery that lies ahead. And yet, despite all this progress, the storms continue to test our ingenuity. Each new detection is a race, not just against fading light, but against our own limitations of time, coordination, and sensitivity. As astronomers refine their instruments and methods, they prepare for the next burst, knowing it may challenge everything we think we know. These efforts ensure that when the next great storm lights up the sky, we will be ready to catch it, to study it, and to let it whisper its story into our collective understanding. From these efforts, we have learned that observation is not passive. It is an active pursuit, of delicate listening, of collaboration across the globe. Each burst captured is the culmination of countless hours of preparation, innovation, and vigilance. The universe does not reveal its secrets easily, but with persistence, we have coaxed open a window into its most violent heartbeats. Through these windows, we glimpse not chaos, but order, patterns of life and death written in the language of light. As we drift further into the journey, we recognize that each storm observed is a reminder of the fragile bridge between us and the cosmos. Above our atmosphere, Instruments hover in silence, waiting. On Earth, telescopes turn their gaze to match the alerts. Across continents, scientists join forces in the shared pursuit of knowledge. The storms do not last, but their echoes endure in data, in memory, and in the heavy elements scattered across galaxies. And in these echoes, we find both wonder and humility. The story continues, for observation is only the beginning. What we record must still be interpreted, woven into theory, and tested against new discoveries. The storms remain as enigmatic as they are beautiful, and each observation leads to more questions. With every step forward, we are reminded that the cosmos is larger, older, and more complex than our imaginations alone could ever capture. The act of observing is both science and meditation, a patient waiting for the universe to speak, and a quiet readiness to listen when it does. And so, as we look ahead, we leave this part of the journey open-ended, a gentle pause in the flow of discovery. The instruments remain vigilant, the telescopes alert, the maps expanding. The storms will continue to blaze and vanish, leaving us with faint traces of their power. What lies beyond these observations is another chapter, another exploration into the unknown. The universe still holds more secrets, and we are not yet done listening. Our journey picks up, as if no time has passed, the memory of colossal explosions still swirling in the cosmic breeze, and drawing us deeper into the secrets that were left lingering in the dark. You can almost imagine the taste of starlight on your tongue as the quiet narrative invites you to imagine matter dancing at speeds that challenge the very structure of time itself. In this pause between breaths, each idea floats like a luminous mote of dust suspended in a sunbeam, and there is a sense of reverence for the forces that shaped those storms. What follows is a continuation rather than a beginning, a gentle leaning into the next layer of understanding that carries the same calm cadence and the same air of mystery. The cosmic fireworks we follow now arise not only from sudden flashes, but from narrow streams of matter, like invisible arrows launched across galaxies and aimed into the deepness of space. These streams, called jets, are produced when a massive star collapses, or when dense remnants like neutron stars spiral together, forming a central engine that can hurl material outward at nearly the speed of light. Imagine a river of particles so energized that each wave of it carries within its pulse a fraction of the universe's raw creation, and you start to appreciate the scale we are dealing with here. They are slender, yet immensely powerful, and when their direction happens to align with our line of sight, we observe them as gamma bursts that last for seconds or minutes, but release unimaginable energies. Inside a collapsing star, gravity compresses the core until it forms a black hole or a magnetar, and this newborn compact object, still swallowing the remains of the star, drives the formation of twin outflows along its rotation axis. If the star's outer layers are thick, the outflow struggles, but with enough rotation and energy, the jets bore through the envelope, punching open channels that let photons and particles escape in a luminous torrent. In a binary merger, two neutron stars, or a neutron star, with a black hole merge into a single object, and the resulting debris disk channels mass into a jet that emerges from above and below the merged core. These different pathways all converge on the same outcome, a narrow, relativistic stream that carries away angular momentum and energy, allowing the central engine to settle while sending a message across the cosmos. As the jet carves its way through the stellar mantle, it drives shocks that heat and accelerate the gas around it, leaving behind a cocoon of energized plasma that spreads sideways from the core of the star. Once the jet emerges from the surface, it experiences a sudden drop in pressure, allowing it to expand freely and accelerate even further, reaching velocities within fractions of a percent of the ultimate speed limit of nature. Such near-light speeds produce extreme effects. Time slows for particles inside the jet, and from our perspective, the radiation is beamed into a narrow cone, intensifying the energy we detect. This beaming effect is why a burst looks so bright to us, and also why most of these jets remain hidden, because unless we sit inside their beam, they whisper quietly in the radio, or remain invisible. When the jet's cone sweeps across Earth, the gamma rays arrive compressed in time and boosted in energy, a consequence of a relativistic effect called Doppler boosting that magnifies the apparent brightness by orders of magnitude. For a brief moment, our detectors see a flash that can outshine entire galaxies, even though the event might be taking place billions of light years away. The duration of the flash depends on how quickly the engine shuts off and on the geometry of the jet, but many bursts last less than a minute, with some as short as a heartbeat. Beyond the initial surge lies a fading afterglow that can persist for days or weeks, carrying information about the environment into which the jet expands. What flows down these cosmic tunnels is not a simple beam of light, but a complex mixture of matter and energy, electrons, positrons, protons, atomic nuclei, and magnetic fields, all locked together in a turbulent dance. In some models, the jet is powered primarily by baryonic matter, meaning the kinetic energy of particles dominates, while in others, electromagnetic fields carry most of the energy in what is called a pointing flux. Regardless of the exact composition, the collisionless shocks within the jet accelerate particles to nearly the speed of light, producing gamma rays through synchrotron radiation and other processes. The resulting radiation is highly variable, flickering as different shells catch up and collide, creating the complex light curves that satellites record. The central engine does not pour out material at a constant rate. Instead, it launches discrete shells at different speeds, so that faster shells slam into slower ones further out, creating internal shocks. These collisions convert some of the bulk kinetic energy into random energy of particles and magnetic fields, giving rise to the prompt emission that we see as the main gamma ray flash. In the internal shock model, each pulse of a burst corresponds to a separate collision event, with rising edges corresponding to the shock heating and trailing edges representing the cooling and expansion. However, not all bursts fit neatly into this picture, and alternative mechanisms such as magnetic reconnection, where tangled field lines snap and rejoin, may also contribute to the observed variability. After the internal collisions have spent their fury, the jet keeps ploughing outward until it encounters the interstellar medium or the wind from the progenitor star, causing a strong external shock. This shock sweeps up material, slows down the jet, and accelerates electrons to high energies, producing synchrotron radiation that spans from X-rays down to radio frequencies. The light emitted at this stage fades smoothly with time and is called the afterglow. It carries information about the density of the surrounding gas and the structure of the jet. Because the jet slows as it sweeps up matter, the beaming angle widens, and eventually the emission becomes detectable, even if we were not initially aligned with the jet's narrow cone. The afterglow reveals itself differently at different wavelengths. High-energy photons fade quickly, while longer wavelengths persist, allowing astronomers to trace the explosion's evolution over days, weeks, and sometimes months. Observations in X-rays, optical, infrared, and radio complement each other, painting a holistic picture of how the jet interacts with its surroundings and how energy is dissipated over time. These multi-wavelength observations also help pin down distances, because by combining the light curve and spectral information, scientists can infer the redshift of the host galaxy. The afterglow is like a slowly fading memory of the initial chaos, a gentle echo that follows the thunderclap of the main burst and provides a window into the environment. Gamma bursts are broadly categorized into long and short types, with the dividing line around 2 seconds, yet this distinction hides a continuous range of behaviors and durations. Long bursts typically last tens of seconds and are associated with the collapse of massive stars that have lost their hydrogen envelopes, while short bursts last fractions of a second and arise from mergers of compact objects. Because the central engines and environments differ, the jets they produce have different structures, energies, and spectral characteristics, which can sometimes blur the boundaries between the categories. Ultra-long bursts and events with intermediate durations complicate the picture even further, suggesting that nature's palette for cosmic explosions is richer than our simple labels. Whenever a jet moves so close to the speed of light, the rules of everyday life give way to the subtle mathematics of Einstein's relativity. For particles racing at such velocities, time dilates and lengths contract, and the radiation we receive is compressed and intensified, altering our perception of the event. Imagine riding along with a photon leaving the jet. In its frame, the burst seems to last longer, while to us, the pulses are squeezed into a fleeting flash. The interplay between relativistic motion and observation is essential to understanding why these blasts appear so bright, and why the energy can be released so quickly from our perspective. If the jet were to be slowed to 1/10 its speed, the energy would be dispersed over a wider angle, and the burst would be much fainter. But the event would last longer and spread across the sky. Our instruments are biased toward detecting the brightest, most collimated events, meaning that we are sampling only a fraction of the true population of bursts. Some estimates suggest that for every burst we detect, hundreds more go unseen because their jets point elsewhere, radiating their energy into the emptiness of intergalactic space. This selection effect is a reminder that our understanding is always mediated by geometry and the limitations of our detectors. The universe hums with activity, even when we do not hear it. Not all jets travel straight. Some precess like spinning tops, causing their beams to sweep across the cosmos in a spiral, which can produce multiple pulses separated by quiet intervals. Astronomers recently observed a burst that produced 3 separate flashes over the course of a day, hinting at a complex engine or perhaps interactions with surrounding debris. Such unusual events remind us that the engines driving these explosions can be erratic, and that our models must accommodate wobbles, instabilities, and renewed energy injection. Each quirk in the light curve is a clue to the underlying mechanism, inviting careful analysis and open-mindedness from researchers who piece together the patterns. Beyond the typical collapsar and merger scenarios, there are rare occasions when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. If the debris forms a disk and conditions are right, jets can erupt from such a tidal disruption event, producing gamma radiation that resembles bursts but with distinctive features. The Einstein probe's observation of an unusual event that did not fit standard burst characteristics may point to such a jetted disruption, illustrating that the universe is full of surprises. Studying these anomalies expands our understanding of jet production and challenges us to refine our theories to encompass a broader range of cosmic cataclysms. When we think of a jet, it helps to imagine a cosmic lighthouse whose beam sweeps across the darkness, only occasionally illuminating the small patch of space where we happen to be looking. For most of its journey, the beam travels through voids and dust clouds without being seen, its energy dissipating into the intergalactic medium. But when it crosses our path, it dazzles. This lighthouse is not anchored on a rocky shore, but on a black hole or neutron star. And its beam is not visible light, but high-energy photons and charged particles. The metaphor underscores the chance alignment required for observation and the sense of awe that accompanies seeing something so rare and powerful. Because jets are collimated into narrow cones, only a small fraction of them point toward us, creating a selection effect that influences our statistics. If the jet is slightly misaligned, we might see only the afterglow or a softer emission, or we might miss the event entirely. Astronomers use theoretical models of jet structure to estimate how many bursts occur for every one detected, correcting for this beaming factor to understand the true rate of such explosions. These corrections show that gamma bursts are far more common than one might think, and that the universe is littered with the remnants of jets that once blazed with ferocious brilliance. Not all jets are equally narrow. Some are tightly collimated like laser beams, while others spread over a wider angle, influencing how their energy is distributed and how bright they appear. A narrower jet packs its energy into a smaller region, leading to higher brightness when viewed head-on, whereas a wider jet appears fainter but can be seen from a larger range of viewing angles. The shape of the jet may depend on the composition of the outflow, the strength of the magnetic fields, and the properties of the progenitor star or merger. By analyzing the decay of afterglow light curves, astrophysicists can infer the jet's opening angle, adding another piece to the puzzle of each explosion. With this understanding of jets in mind, we can appreciate that these beams of matter racing at nearly the speed of light are the veins through which gamma bursts express their fury. They are not random. They are shaped by the physics of their engines and the environment that surrounds them, and their behavior holds clues to deeper principles. To fully grasp their nature, we must look at the invisible threads that guide them, the magnetic fields that thread the progenitor, and tie the jets into coherent structures. In the next phase of our exploration, we gently turn our attention to those magnetic forces, continuing the same slow rhythm of inquiry that has brought us this far. Magnetic fields are invisible, yet powerful, threading through stars and the vacuum of space like cords of tension that can twist, snap, and reconnect with explosive results. In everyday life, we rarely think about these fields. A compass needle aligning with Earth's magnetism is a gentle reminder, but in an astrophysical jet, the stakes are far higher. Here, magnetic lines of force can channel energy, confine particles, and resist instabilities, shaping the jet's geometry and influencing how and when the energy is released. Understanding the role of these invisible lines is essential for unraveling the chaos of gamma bursts, and it adds an additional layer of depth to our journey. Inside a massive star, convection and rotation can amplify primordial magnetic fields, winding them up like springs as the core spins faster during collapse. When the core collapses to form a black hole or a magnetar, these fields can be amplified to incredible strengths, twisting around the nascent object and driving the extraction of energy from its rotation. The result is a magnetized disk and a pair of magnetic funnels along the rotational axis, which provide the channels through which jets emerge. If the magnetic field is strong enough, it can even dominate the dynamics of the outflow, turning kinetic jets into electromagnetic beams. In a Poynting flux-dominated jet, most of the energy is carried by the electromagnetic field, rather than by the motion of matter, and the field lines themselves act as the conduit. The electromagnetic energy travels along twisted field lines that spiral out from the engine, and if those lines dissipate through reconnection or instabilities, the energy can be converted into radiation. This scenario contrasts with baryonic jets, where kinetic energy of particles provides the main reservoir, and internal collisions between shells are responsible for the primary energy dissipation. Deciding which mechanism dominates in a given burst is an active area of research, with evidence suggesting that both play roles in different contexts. Magnetic reconnection occurs when opposite field lines meet and annihilate, releasing stored magnetic energy as heat and kinetic energy of particles. In the environment of a gamma burst jet, reconnection may occur in current sheets that develop due to rotation and shearing motions, sparking miniature explosions within the larger explosion. These reconnection events could explain the rapid variability seen in some bursts, as they can produce short, intense spikes of emission without requiring the engine to change its output. They also help to accelerate particles to ultra-relativistic energies, feeding the reservoir of electrons and positrons that radiate in gamma rays. Magnetic fields can act like a coil of wire around a jet, confining the outflow and preventing it from spreading out too quickly. The degree of collimation depends on the balance between magnetic pressure and the pressure of the hot plasma, with stronger fields producing narrower jets. This is why jets from some progenitors may be slender, and those from others may be broader. The difference may reflect variations in the initial magnetization and rotation. Observations of afterglow light curves help us infer these properties by revealing how quickly the jet spreads and how the beaming evolves over time. A highly magnetized jet is not necessarily stable. It can develop kinks and instabilities, similar to the twisting of a water hose under pressure. These instabilities can cause the jet to bend or wobble, altering the direction of its beam and perhaps causing the precession we discussed earlier. They also induce turbulence within the jet, mixing magnetic and kinetic energy and providing additional avenues for dissipation. In this turbulent interior, ordered fields coexist with chaotic motions, and the interplay between them determines the patterns of the emitted radiation. Electrons spiraling in magnetic fields emit synchrotron radiation, producing a broad spectrum that includes the gamma rays we detect from bursts. The energy of the radiation depends on the strength of the magnetic field and the energies of the electrons. Stronger fields yield higher frequency radiation. Magnetic fields also enable inverse Compton scattering, where electrons transfer energy to low-energy photons, boosting them into the gamma-ray regime. Thus, magnetism not only shapes the dynamics of jets, but also serves as the mechanism by which kinetic energy becomes visible light and high-energy photons. Some models propose that jets can also be driven by neutrino annihilation above the accretion disk around a black hole, creating a baryonic wind that becomes collimated. In such cases, the role of magnetism may be secondary, but even here, magnetic fields are likely to play a role in shaping the outflow and in accelerating particles. Comparing neutrino-driven and magnetically driven jets helps us understand the diversity of burst behaviors and why some events are more energetic or longer-lived than others. Ultimately, observations of polarization, spectral shape, and variability can hint at the relative contributions of magnetic and neutrino mechanisms. One way to probe the magnetic fields in jets is to measure the polarization of the emitted light, because ordered fields produce a preferred orientation. Some bursts show significant polarization, implying the presence of coherent magnetic structures, while others show none, suggesting a more chaotic or tangled field. The degree of polarization can change over the course of a burst, indicating evolving magnetic geometry as the jet expands and interacts with its surroundings. Future instruments with better sensitivity to polarization may provide deeper insights into the magnetic anatomy of these explosions. In some scenarios, a highly magnetized neutron star, known as a magnetar, acts as the central engine of the burst. These objects possess magnetic fields trillions of times stronger than Earth's, and their rapid spin can drive a wind that becomes a jet. The magnetic energy stored in such a star can be enormous, and as the star spins down, that energy is transferred into the outflow. Whether magnetars or black holes dominate the population of burst engines remains an open question, and both are likely to contribute under different conditions. When two neutron stars merge, their combined magnetic fields can tangle and amplify, potentially generating a large-scale field that guides the resulting jet. Simulations suggest that the shearing motion of the merging stars twists the field into a torus around the merged object, while turbulence helps to organize the field on large scales. This process is important because a stable large-scale field is thought to be necessary to launch a relativistic jet and sustain it long enough to produce observable gamma radiation. Recent detections of gravitational waves associated with short bursts, provide evidence that such mergers produce jets, confirming the role of strong magnetism in at least some cases. Around the central engine, matter spirals into an accretion disk that can amplify magnetic fields through turbulence and differential rotation. These amplified fields can connect the disk to the black hole, extracting rotational energy via a process known as the Blandford-Znayak mechanism, which may power some jets. The same fields can also drive winds from the disk itself, which might contribute to the early emission or shape the environment into which the jet expands. Understanding the interplay between disk magnetism, accretion, and jet launching remains a vibrant area of theoretical and computational research. Magnetic fields act like brake pads on the rotating core or disk, converting rotational energy into electromagnetic energy that flows outward along the jets. This extraction of energy slows the spin of the central engine while powering the outflow, linking the destiny of the engine to the brightness of the burst. If the field is weak, the engine may retain more of its spin and produce a weaker jet, whereas a strong field can drain the spin quickly and produce a powerful but shorter-lived jet. These subtleties in energy extraction illustrate how intimately magnetism is tied to the longevity and ferocity of cosmic explosions. Inside the jet, magnetic fields are responsible for accelerating charged particles through shock acceleration and reconnection, processes that operate efficiently in relativistic conditions. In shock acceleration, particles gain energy by repeatedly crossing a shock front. In reconnection, they ride along newly formed field lines as they snap into place. Both mechanisms can produce particles with energies far beyond those achievable in human-made accelerators, making gamma bursts natural laboratories for high-energy physics. Through these mechanisms, magnetism not only steers the outflow, but also energizes the very particles that emit the light we see. As jets propagate and interact with their environment, they generate turbulence that cascades across scales, mixing magnetic energy with kinetic energy in a stochastic manner. Turbulence can tangle field lines, reducing polarization and enabling reconnection in small regions, which may contribute to the variability of bursts. The chaotic mixing also helps distribute energy throughout the jet, preventing any one region from becoming too dominant and maintaining a sort of dynamic equilibrium. Recognizing this interplay between order and chaos is essential for understanding why bursts are both structured and unpredictable. Once the jet has deposited its energy into the interstellar medium, the magnetic fields do not simply vanish. They can seed the surroundings with ordered structures. These fields may contribute to the overall magnetization of the host galaxy, or stimulate the growth of cosmic rays that propagate far from the explosion site. Thus, the influence of gamma bursts extends beyond their brief lifetimes, leaving magnetic fingerprints that may shape subsequent star formation or the propagation of charged particles. Even at these distances, the interplay between magnetism and matter remains a source of fascination and ongoing study. In every corner of this story, magnetic fields appear as the scaffolding around which the chaos of an explosion finds some coherence. Whether they channel jets, accelerate particles, or shape light curves, they are essential to understanding how such violence can produce such beauty. By contemplating these invisible lines, we add a layer of texture to our picture of gamma bursts, making the unseen forces visible in our imagination. This delicate dance between order and chaos sets the stage for our next reflection on the sheer energy involved in these events. As we let the notion of magnetism settle, the mind naturally turns to the magnitude of the energies at play, energies that dwarf anything we can easily comprehend. Relativity and magnetism work together to unlock reservoirs of power beyond our everyday experience, and it is time to compare that power with more familiar cosmic phenomena. In the same measured cadence, we will explore what it means to say that a burst releases more energy than a star can, in billions of years. Let us step gently into that realm of comparison and continue our journey without haste, like travelers who savor each moment of a long voyage. Talking about the energy of a gamma burst is like talking about the energy of creation itself. The numbers are so large that they challenge the boundaries of language. For perspective, consider that our sun will shine for 10 billion years, releasing a steady outflow of photons and warmth. Yet some bursts release more energy in a matter of seconds. When we say that a burst shines hundreds of times brighter than a typical supernova and 1,000,000 trillion times brighter than the sun, we are invoking comparisons that demand a deep breath. These comparisons are not meant to intimidate. They are meant to anchor us, to provide stepping stones across a sea of magnitudes. A classical supernova releases on the order of 10 to the 44th joules of energy over weeks, an amount that would destroy any planetary system unlucky enough to be nearby. A gamma burst compresses a similar or even larger amount of energy into a timescale of seconds, making its power output far greater than that of a supernova at any moment. This is why the prompt emission appears so blindingly bright. The power is concentrated both spatially, in a narrow jet, and temporally, in a brief flash. Even the afterglow, though it fades quickly, can outshine the host galaxy in some wavelengths for a day or two, a testament to the extraordinary energy reservoir of the burst. Quasars, powered by supermassive black holes accreting matter over millions of years, can emit enormous amounts of energy, but their luminosity is spread out over long timescales. If a quasar radiates continuously, it may eventually outshine a single gamma burst when integrated over its lifetime. But in terms of instantaneous power, bursts are among the brightest things the universe produces. The difference is like comparing the gentle, continuous flow of a great river to the sudden, roaring release of a dam. Both carry water, but the burst is all momentum and spray. This analogy helps us understand why gamma bursts, though fleeting, capture the imagination of astronomers and challenge the limits of our detectors. The source of this energy lies in the gravitational potential of massive stars and in the binding energy of neutron stars, energies that are liberated when matter collapses into the most compact states allowed by physics. When a massive star's core collapses, it releases a flood of neutrinos and photons, but only a small fraction of the total gravitational energy escapes. The jet taps into that reservoir and channels it outward. In a merger, the orbital energy of two compact objects becomes kinetic energy and eventually electromagnetic radiation, again with the jet serving as the conduit. Thus, bursts are cosmic machines for converting gravitational binding energy into high-energy light, operating with astonishing efficiency and speed. Because the energy is focused into a narrow jet, the isotropic equivalent energy, the energy inferred if the burst were radiating in all directions, is enormous, even though the true energy may be more modest. This distinction matters. A jet with a narrow opening angle of a few degrees may have a true energy 100 times less than its isotropic equivalent, but observers do not perceive that difference. Understanding the opening angle therefore helps refine our estimates of the total energy budget and influences our comparisons with other astrophysical events. By combining observations of the jet break in afterglow light curves with theoretical models, scientists can derive this angle and compute the true energy release. Not all bursts are created equal. Some release energies approaching 10 to the 54th ergs, while others barely reach 1,000th of that value. This diversity reflects differences in progenitor mass, rotation rate, magnetic field strength, and the density of the surrounding environment. There are also bursts with unusually long durations and moderate energies, and those with multiple pulses that may indicate sustained engine activity or repeated injection of energy. Each event is a natural experiment, offering insight into how nature organizes energy on the grandest scales and how slight differences in initial conditions can lead to vastly different outcomes. Our sample of bursts is biased toward those with high isotropic equivalent energies because they are easier to detect, while faint or off-axis bursts often go unnoticed. When we account for this bias, the distribution of true energies becomes narrower, suggesting that most bursts release comparable amounts of energy when beaming is considered. This finding hints at underlying commonalities in the physics of jet launching across different progenitors, pointing to universal processes at work, regardless of the environment. Even so, exceptional events like the record-breaking burst in recent years show that nature occasionally pushes to extremes beyond the typical energy range. To bring these numbers closer to human experience, imagine that a single burst releases as much energy as the sun will emit over its entire lifetime, but condenses it into the duration of a song. If you could somehow capture a fraction of that energy, it would vaporize our planet or obliterate our atmosphere. Yet in reality, these bursts occur so far away that their effect is usually harmless. Only if such a jet were to point almost directly at Earth from within our own galaxy would we face a threat, and even then the probability is small. These thought experiments highlight both the staggering power of gamma bursts and the protective buffer provided by the vastness of cosmic distances. While a burst's energy is enormous on human scales, it is a tiny fraction of the energy content of a galaxy, so its impact on the host's overall luminosity is fleeting. On the timescale of the burst, it can temporarily outshine all the stars in its host, but the galaxy soon returns to its normal state as the afterglow fades. The energy does, however, deposit heat and momentum into the surrounding gas, potentially triggering or quenching star formation in local regions. By comparing multiple bursts in different galaxies, researchers are exploring how these explosions contribute to galactic ecology over cosmic time. Some of the energy in a burst goes into accelerating protons and heavier nuclei to nearly the speed of light, potentially contributing to the population of ultra-high energy cosmic rays that reach Earth. These particles carry with them chemical signatures of their origin and may complement the neutrinos and photons that we detect from distant bursts. The cosmic rays travel for millions of years, bending through intergalactic magnetic fields that twist their paths before they finally reach detectors here on Earth. In this way, the energy released in a brief flash continues to influence the cosmos long after the afterglow has faded, carrying information across distances that dwarf our imagination. Burst energy also emerges as torrents of neutrinos, ghostly particles that rarely interact with matter, but carry away a significant fraction of the gravitational energy released during collapse or merger. Detectors buried in Antarctic ice or deep underground may one day catch these neutrinos, providing an independent channel to study the energy budget of bursts. Because neutrinos travel almost unimpeded through the universe, they carry pristine information about the conditions deep within the engine, complementing what we learn from photons. The combination of neutrino, photon, and gravitational wave observations is transforming gamma bursts into multi-messenger laboratories for fundamental physics. When two neutron stars spiral together, they emit gravitational waves that ripple through spacetime, carrying away orbital energy and causing the stars to draw closer. By the time the stars merge and produce a burst, the gravitational waves have already told us when and where to look, providing context for the subsequent emission. The detection of gravitational waves from GW170817 and the associated burst was a watershed moment, revealing that these phenomena are linked and confirming theoretical predictions. As more events are observed, the synergy between gravitational wave detectors and gamma-ray satellites will sharpen our understanding of energy release in the universe's most violent collisions. Among cosmic fireworks, only the Big Bang itself dwarfs the brightness of gamma bursts when scaled by time, for nothing else seems to compress so much energy into such a brief window. Supernovae, quasars, magnetars, and tidal disruption events all contribute to the cosmic energy budget. But gamma bursts stand apart because of their extreme power-to-duration ratio. If we consider the integrated energy over the life of a quasar, it may surpass that of many bursts, yet the quasar's light is diffused over eons and seldom threatens life in the way a nearby burst might. By placing bursts within this hierarchy, we sharpen our appreciation of the spectrum of cosmic energetics and see how nature organizes power across different scales. Reflecting on these comparisons, we sense the true scale of the cosmic artillery, and yet we cannot help but wonder what such energies might do if pointed closer to home. Our curiosity naturally turns to the question of risk. Could a burst damage the delicate balance of life on Earth? And what would that mean for humanity? As we move into the next part of our exploration, we will gently examine the potential threats without losing the calm cadence of our narrative. The energy we have been admiring has a darker side, and we will now look at how that side may influence the history of our planet. The idea of energy beyond comprehension becomes more tangible when we consider its potential to affect living worlds, including our own pale blue dot. A burst aimed at Earth could have consequences, not through heat or direct radiation, but through its effect on the delicate atmosphere that makes life possible. To explore this possibility, we must move slowly and carefully, balancing scientific seriousness with an appreciation for the rarity of such an event. We will let the facts speak in gentle tones, allowing us to ponder without succumbing to fear or sensationalism, and to remember that probability and distance are our allies. When high-energy photons from a burst hit Earth's atmosphere, they would not burn the surface directly. Instead, they would break apart molecules and generate nitrogen oxides. These compounds can catalyze the destruction of ozone, the protective layer that absorbs ultraviolet light, leading to a thinning or even collapse of the ozone shield. Without ozone, the sun's ultraviolet radiation would reach the ground in deadly abundance, damaging DNA and disrupting ecosystems across the globe. The severity of the effect would depend on the total fluence of gamma rays, which in turn depends on the distance and orientation of the burst. Some researchers have suggested that past mass extinctions on Earth may have been triggered by distant bursts that depleted the ozone layer and caused a cascade of biological consequences. One proposed candidate is the Ordovician extinction around 440 million years ago, during which marine life suffered a dramatic die-off that could be consistent with a sudden increase in ultraviolet radiation. However, evidence for such a link is indirect, and many other factors could have contributed. The idea remains a hypothesis among many. Even if true, these events would be exceedingly rare, perhaps occurring only once or twice in Earth's half-billion-year history. Estimates suggest that a fluence of around 100 kilojoules per square meter might destroy most of the ozone layer within months, a level requiring the burst to be within a few kiloparsecs of Earth. At greater distances, or with the jet slightly misaligned, the fluence drops dramatically, reducing the potential damage to the point where life would hardly notice. Because bursts radiate into narrow beams, the chance of one being aimed exactly at us is small, further diminishing the risk. Thus, while the mechanism of ozone depletion is understood, the likelihood of it occurring in our cosmic neighborhood is low and should be kept in perspective. Long bursts are most often observed in small, irregular galaxies with low metal content, environments where massive stars lose less mass and retain the rapid rotation needed to power jets. The Milky Way is richer in heavy elements, causing massive stars to shed their outer layers and angular momentum, making collapsar-type bursts much rarer here. Observations from the Hubble Space Telescope suggest that long bursts like those seen in distant galaxies are exceedingly uncommon in spiral galaxies like ours. Short bursts from mergers are possible in the Milky Way, but they are brief, and their jets are narrower, further lowering the risk of direct impact. Calculations combining the rate of bursts, the size of the galaxy, and the beaming angle estimate that the probability of a damaging burst hitting Earth within the next billion years is small. One study suggests that the chance that Earth has been hit by a dangerous burst in the past 500 million years is around 50%, meaning that even if such events occur, they are separated by hundreds of millions of years. This uncertainty arises because we cannot know the orientation of past jets or the precise rate of bursts in the Milky Way. Nevertheless, the combination of rarity, orientation, and distance provides comfort that such events are not imminent, and that life has persisted despite past cosmic storms. Even if a burst were to deplete the ozone layer, life on Earth would not necessarily be extinguished. Aquatic organisms and those living underground or underwater might survive. Evolutionary processes could lead to new forms of UV-resistant life, and ecosystems could recover over geological timescales, as they have after other mass extinctions. In this way, bursts may have played a role in shaping the diversity of life by imposing sudden stresses that drove adaptation and diversification. Contemplating this possibility invites us to view cosmic catastrophes not only as threats, but also as catalysts for change and drivers of evolutionary innovation. Mergers of neutron stars produce short bursts, and though their jets are narrower and their total energy somewhat lower, they are also located preferentially in older stellar populations, like those in our galaxy's halo. Some older stars, captured from dwarf galaxies, might retain low metallicity, potentially giving rise to long bursts, even in a spiral galaxy. But the number of such stars is small. Thus, short bursts are more probable than long bursts in our vicinity, but their narrow beams and limited energy make them less likely to cause widespread damage. Even so, monitoring nearby star clusters and potential merger progenitors remains a part of our early warning system and a reminder of our connection to the larger cosmos. Aside from ozone depletion, bursts could also shower Earth with cosmic rays that might penetrate our atmosphere and generate secondary particles at ground level. These secondary showers could slightly increase mutation rates or disrupt electronic systems, but the Earth's magnetic field and atmosphere provide significant shielding. In any case, cosmic rays from supernovae and the Sun are already part of our environment, and the additional contribution from a distant burst would be minor. Thus, the primary concern remains the effect on ozone and ultraviolet light, rather than direct particle bombardment, and even that concern is tempered by probability. Orientation is our ally. The narrowness of jets means that only a small slice of the sky is ever at risk from any given burst. Distance is another ally. Because gamma rays spread out with distance, even a slight increase in distance reduces the fluence by the square of that distance. Together, these factors ensure that the overwhelming majority of bursts occur without any effect on Earth, no matter how powerful they may be. This knowledge allows us to appreciate the beauty of these events without undue fear, savoring their splendor as expressions of cosmic power rather than as threats. Modern instruments like the Swift satellite, Fermi, and ground-based observatories monitor the sky continuously, ready to capture bursts and alert the scientific community within seconds. If a burst were to occur nearby, these instruments would provide warning and enable the study of its effects in real time, offering invaluable data. Such monitoring is not only a scientific pursuit, but also a form of planetary stewardship, ensuring that we are aware of rare cosmic events that might impact our world. By watching the universe, we gain both knowledge and a sense of security, knowing that we are attentive to the heavens that have shaped our history. Even as we consider the fragility of Earth, it is worth remembering that our planet has survived for billions of years in a dynamic cosmos. Comets, asteroids, supernovae, and perhaps bursts have all left their mark. Yet life has persisted, adapted, and flourished. This resilience gives us confidence that the universe is not actively hostile, but simply indifferent, and that our greatest challenges may come from within rather than from above. With this balanced view, we can continue exploring the physics of bursts while remaining grounded in an appreciation for life's tenacity and the quiet strength of our planet. As the threat fades in our mind, replaced by scientific curiosity, we can now shift our gaze back to the fundamental lessons these bursts teach us about physics under extreme conditions. Knowing that these storms seldom reach us allows us to revel in their strangeness and to use them as laboratories for understanding the universe. Each burst is a natural particle accelerator, a gravity probe, and a magneto-hydrodynamic experiment rolled into one, providing data we cannot reproduce on Earth. We proceed forward with respect and wonder, ready to learn what these extremes reveal about the laws of nature and about ourselves as seekers of knowledge. The next section of our journey will explore how gamma bursts serve as laboratories for physics, testing our theories and pushing the boundaries of human understanding. The calm tone remains, but our attention shifts from the risk to the rich opportunities these phenomena offer to modern science. Bridging observation and theory, we will examine what extreme pressure, energy, and density can teach us about the fundamental forces, and how we can learn from nature's own high-energy experiments. This gentle transition leads us into a realm where curiosity thrives, and where each observation becomes a window into the fundamental workings of reality. Studying the host galaxies of bursts helps refine our understanding of risk, because the prevalence of bursts depends on star formation, metallicity, and galaxy morphology. Small, metal-poor galaxies produce bursts more frequently than massive spirals like the Milky Way, reflecting differences in stellar evolution and rotation rates. Our location within a large, metal-rich galaxy thus reduces our exposure to bursts, while also offering the opportunity to observe distant events unobscured by our own activity. By mapping where bursts occur, astronomers can build statistical models of their distribution and forecast how often they might appear in different cosmic neighborhoods. Metallicity refers to the abundance of elements heavier than helium, and it influences how stars lose mass through winds during their lives. In low metal environments, stars retain more mass and angular momentum, making their cores more likely to collapse into rapidly spinning black holes, capable of launching jets. Conversely, high metal stars lose mass and angular momentum, reducing the chance of forming a collapsar with the required rotation. This subtle interplay of chemistry and physics underscores why bursts are not evenly distributed throughout the universe, adding another layer to our appreciation of cosmic diversity. Though the risk is low, considering it helps us appreciate the fragility of our biosphere and the importance of planetary protection and awareness of cosmic hazards. Such awareness can motivate further investments in space weather monitoring, atmospheric studies, and understanding of the sun's variability, which pose more immediate threats. In this sense, gamma bursts serve as a reminder that our planet is not isolated, but part of a dynamic cosmos that occasionally touches our shores. They also remind us to cherish the stability we experience, and to recognize that life has endured past upheavals through resilience and adaptability. Contemplating cosmic threats can evoke a subtle tension between awe and vulnerability, a feeling of being small under the vastness of the night sky. Yet there is comfort in knowing that these events are rare, and that they contribute to the rich tapestry of processes that have shaped our universe. The very same bursts that might harm also create heavy elements, drive galaxy evolution, and light up the cosmos with beauty and information. Holding these opposing thoughts together without panic is part of the balance we cultivate in this gentle journey, allowing wonder to coexist with caution. Having considered the threats, we can now turn fully to the opportunities that gamma bursts present as laboratories for extreme physics, exploring conditions unreachable on Earth. Each burst offers a snapshot of matter and energy pushed to their limits, and by studying them, we can probe theories in ways no human-made experiment can match. The quiet pace of our narrative carries us into a domain where gravity, magnetism, quantum mechanics, and nuclear physics intersect and speak through light and time. What lessons can be drawn from these cosmic laboratories, and how do they inform our understanding of the universe and our place within it? The rapid acceleration and intense gravity near the central engine provide a natural testbed for Einstein's theory of general relativity, probing strong field regimes far beyond our solar system. How space and time behave around a newly formed black hole, and how energy is extracted from its rotation, can be inferred from the timing and spectrum of the emitted light. Observing the ringdown of gravitational waves from mergers, in concert with the accompanying burst, can reveal the mass and spin of the resulting black hole, and test the no-hair theorem. These observations complement those of black hole binaries, and offer another channel to scrutinize our understanding of gravity in the wild. Short bursts arising from neutron star mergers provide clues about the dense matter inside neutron stars and the equation of state that describes how such matter behaves. By measuring the delay between the merger and the burst, and by modeling the gravitational wave signal, scientists can infer whether a hypermassive neutron star formed temporarily before collapsing into a black hole. This, in turn, constrains the maximum mass a neutron star can support and the stiffness of nuclear matter at densities far beyond those of atomic nuclei. Every observed event tightens these constraints, incrementally building a picture of matter at extreme pressure and helping to calibrate nuclear theory. Burst jets accelerate particles to energies beyond those produced in Earth-based accelerators, making them natural sources of ultra-high energy cosmic rays. The mechanism of acceleration, whether through shock waves, magnetic reconnection, or turbulence, remains an active question, and bursts offer a laboratory to distinguish these processes. By comparing observed spectra of cosmic rays with models of burst acceleration, researchers hope to uncover the origins of the most energetic particles in the universe. These efforts show how astrophysics and particle physics intersect, with cosmic events informing fundamental physics questions and guiding the design of future experiments. Gamma bursts provide environments where magnetic fields reconnect under conditions unattainable in laboratories, offering insights into plasma physics and the behavior of relativistic particles. The rate at which reconnection proceeds, the efficiency of particle acceleration during reconnection, and the structures of the resulting current sheets are key open questions. High time resolution observations of bursts can test theories of reconnection, with each spike in the light curve potentially corresponding to a reconnection event. In this way, bursts function as cosmic plasma laboratories, complementing solar flares and magnetospheric substorms in our solar system. The photons emitted in a burst travel through an environment with extremely high densities, magnetic fields, and velocities, allowing us to test models of radiation transport. Some bursts exhibit thermal components in their spectra, hinting at a photosphere where the jet becomes optically thin, while others display non-thermal spectra shaped by synchrotron and inverse Compton processes. Understanding these spectra helps us determine how and where energy is dissipated in the jet and what the dominant emission mechanisms are, enriching our knowledge of radiation physics. Each spectral feature is a clue, and each observation an opportunity to refine our theoretical frameworks and challenge our assumptions. The structure of jets, whether they are uniform, have a core and sheath, or are stratified in energy, affects how they interact with the environment and what we observe. By modeling the afterglow and comparing it with data, scientists infer whether jets have sharp edges or gradual wings, and whether the energy per unit angle varies across the jet. These details, though subtle, influence how we estimate total energy and how we relate bursts to their progenitor stars or mergers. Ongoing observations with radio interferometers and X-ray telescopes continue to refine our understanding of jet structures, bridging theory and observation in a harmonious way. Because bursts are visible across vast distances, they serve as beacons that illuminate the early universe, allowing us to probe star formation and galaxy evolution at high redshift. The redshift of a burst tells us how long ago the explosion occurred, and by studying bursts at different redshifts, we can reconstruct how the rate of massive star formation has changed over cosmic time. These data complement other cosmological probes and help calibrate models of reionization, chemical enrichment, and the growth of structure throughout cosmic history. Thus, bursts serve not only as physics laboratories, but also as lighthouses that guide our understanding of the universe's evolution. Researchers have explored whether certain correlations in burst properties could make them into standard candles, tools for measuring cosmic distances. Correlations between the peak energy of the spectrum and the luminosity, or between variability and brightness, hint at underlying regularities. If calibrated properly, these relations could extend the cosmic distance ladder to redshifts beyond those reachable with supernovae. However, intrinsic scatter and evolutionary effects complicate this endeavor, and bursts remain challenging as cosmological tools despite their potential. The coupling of gamma-ray observations with gravitational waves, neutrinos, and even optical transients exemplifies a new era of multi-messenger astrophysics unfolding before our eyes. Each messenger carries different information: gravitational waves about mass and motion, neutrinos about core processes, photons about magnetism and radiation. Combined, they offer a holistic view of the event and cross-check each other, reducing uncertainties and revealing hidden aspects. This synergy multiplies the scientific return of each observation and exemplifies the collaborative nature of modern science, where different detectors speak a common language. As our catalogue of bursts grows, so too does the diversity of their properties, challenging simple classification schemes and requiring more nuanced categories. Intermediate duration bursts, ultra-long bursts lasting thousands of seconds, and bursts with extended emission blur the line between long and short categories. Some events seem to combine features of both collapsar and merger scenarios, suggesting that nature operates along a continuum rather than in discrete boxes. Machine learning and statistical methods are being applied to unravel patterns in this diversity, pointing toward a more physical classification based on progenitor and environment. Despite decades of study, many aspects of bursts remain mysterious. The composition of the jet, the exact mechanism of energy dissipation, and the triggers for the central engine's variability. Are jets always present in collapses, or do some explosions fail to produce them, resulting in observationally faint events that escape detection? What determines whether a merger produces a black hole directly or a hypermassive neutron star first? And how does this choice affect the burst and its afterglow? These unanswered questions keep the field vibrant and ensure that each new observation adds fresh clues to the puzzle rather than a final answer. Advances in detector technology are opening new windows on bursts, with instruments like the Einstein probe, the James Webb Space Telescope, and next-generation gravitational wave observatories poised to provide unprecedented data. Faster alert systems, broader spectral coverage, and higher sensitivity will allow us to catch fainter and more distant events, filling in gaps in our understanding. Multi-wavelength campaigns involving dozens of telescopes across the globe and in orbit will become more common, reflecting the collaborative nature of burst science. These technological strides promise to transform our knowledge and to reveal nuances that current instruments can only hint at, continuing the cycle of discovery. Beyond physics, bursts inspire wonder and curiosity. They remind us that the universe is both violent and beautiful, and that human ingenuity can unlock its secrets. Students and amateur astronomers alike follow alerts, watch afterglows fade, and participate in real-time science, building a community around these cosmic beacons. In classrooms, bursts serve as a gateway to discussions about relativity, nuclear physics, cosmic evolution, and our place in the universe. Thus, they are not only objects of research, but also catalysts for learning and imagination, connecting people of all ages to the cosmos. When we meditate on gamma bursts, we are confronted with the extremes of nature, and this confrontation can provoke introspection about scale, time, and significance. They challenge us to think beyond human lifetimes, and to grasp the idea of energies far beyond what we could ever harness or need. At the same time, their fleeting nature reminds us that even the most violent events leave only transient footprints in the cosmic tapestry. Holding these thoughts gently in mind can deepen our appreciation for both the fragility and the resilience of the universe, and for our ability to comprehend it. There is a humility that comes from studying things we cannot control, like gamma bursts, because they remind us that we are small participants in a vast drama. Yet there is also empowerment in the knowledge that we can understand these events through careful observation and analysis, and that our intellect bridges the gap between us and the stars. This combination of humility and empowerment is a hallmark of science, and one of the reasons it resonates so deeply. In contemplating bursts, we thus find both a mirror and a window, a mirror reflecting our yearning to know, and a window opening onto the unknown. Looking ahead, we anticipate that new discoveries will refine our understanding and also bring fresh surprises, because the universe seldom conforms to our expectations. Perhaps we will find classes of bursts we have not imagined, or physical processes that challenge current theories and open new avenues of inquiry. Whatever emerges, we will approach it with the same calm curiosity and the same respect for the unknown, trusting that each revelation expands our world. The story is ongoing, and we are fortunate to be listeners, participants, and interpreters of the cosmic tales that unfold in the night. As this section draws to a close, the narrative does not resolve, but rather lingers, like the afterglow of a burst, ready to merge into the next phase of our journey. We have explored jets, magnetism, energy, threats, and lessons, but there are still more stories to tell and more wonders to consider in the chapters ahead. The pace remains steady, the tone remains gentle, and the path ahead remains open, inviting our curiosity to wander further. With no final conclusion, this part fades into the next, leaving us poised to continue our exploration with attentive hearts and open minds, ready to be surprised. The echoes of these cosmic storms will resonate into the following segments, seeding questions and possibilities that will unfold at a leisurely pace. Each thought we have entertained whispers to another thought yet to come, and each concept we have touched leaves a trace that will guide our hands through the unseen fabric of the universe. We carry forward the threads of relativity, magnetism, and cosmic danger, weaving them into a tapestry that stretches beyond what we have already seen. In the coming moments, those threads will intertwine with new patterns, forming a continuation that is both familiar and freshly intriguing. It is a reminder that our understanding is a living thing, growing with every observation and evolving with every whisper from the cosmos. The stories we have told about jets and fields and energies are not fixed, but rather they shift as new evidence arrives, and old theories make way for richer explanations. In this gentle narrative, we will honor that dynamism, allowing uncertainty to sit comfortably beside knowledge, and letting each answer be a doorway rather than a wall. In doing so, we maintain the sense of wonder that has carried us thus far and will carry us still deeper. As you drift through this narrative, imagine the feeling of floating between stars, knowing that the tale will continue beyond your current horizon. The sensation of suspended discovery, of being between what is known and what is yet to be revealed, is itself part of the pleasure of inquiry. We resist the urge to conclude, because the story is alive, and to close it would be to deny the flow of the universe that ceaselessly renews itself. Instead, we linger in this liminal space, content to let the next chapter emerge in its own time. We now stand on the edge of that emergence, not with finality, but with anticipation, ready to see how the themes of power, light, and cosmic interplay will develop. There is no need to rush, no need to compress these giant scales into a moment. We have the luxury of time and the permission to wander. Just as the afterglow of a burst gradually reveals layers of complexity, so will the ensuing portions of our journey reveal deeper insights and unexpected connections. With this awareness, we gently leave this segment behind and turn our attention forward, letting the narrative carry us onward as softly as a whisper across an eternal night.